In the last module, that is the define phase, we discussed about the basic and fundamental principles of Six Sigma. Then we also went into the depth about the define phase of the Six Sigma. What are the different activities we are doing, like selecting the appropriate projects, then creating the project charter to give a clear explanation of what is the problem, what is the goal we want to achieve, what is the timeline, what is going to be the benefits, what is going to be the scope of the project, and all this we documented in the project charter. And then we also saw how we are going to do the high level process mapping. So at the end of define phase, we have clearly identified a project, and for that project what is the current problems and what we want to achieve, that is very clear. So now we move on to the next module, that is the measure phase of the Six Sigma project. So in the measure phase, we actually collect a lot of data so that we are going to have some data for analysis, so that using the data so in the measure phase, we are going to collect a lot of data. As I have told you during the basics of Six Sigma, we have seen that Six Sigma is a data driven approach. So in the measure phase, we collect a lot of data, and then using this data, we are going to analyze what is going to be the root cause of the problem, and we are going to find the solutions. So in the measure phase, we are going to collect the data. So whenever you are collecting the data, we are going to analyze. There are two types of analysis we are going to do. One is what we call it as a process analysis. So the first one is the process analysis, and the second one is the data analysis. So in process analysis, what we are going to do is we are going to do a minute details analysis of what is happening in each and every process, and then whether there are any opportunities for simplifying the process so that we can improve the efficiency of the process. So that is the purpose of doing the process analysis. And so we will be learning in this tool what are the different tools which will help you to collect the data so that you will be able to do the process analysis. And the second type of the analysis you will be doing at the analysis phase is the data analysis. So here what we are going to do is we are going to collect a lot of transactional data, and using this data we will just use these statistical tools and some graphical tools so that we will be able to represent these problems in a graphical format, and then we can analyze what are the problems, and then we can solve those problems. So the data analysis mainly is used using the statistical tools. So I will just give an example of what we are trying to do in the data collection in the measure phase. Say for example, you are having a process having 5 steps. So step 1, step 2, step 3, step 4 and step 5. So you are finding that in this 5-step operation, there is always a delay in your deliveries, and you are measuring say for example, this is a start process and this is the end process, and to your customer you are committing a certain delivery dates, and then at the end of the month, whenever you are measuring the on-time delivery, you are finding that your on-time delivery is only 85%, whereas the customer requirement is 95% minimum. So now since you have this problem, you are taking this as a Six Sigma project to understand what are the problems and do the improvements. Okay. So in this, again during the measure phase, so what type of data need to be collected, you will have to be very clear. So in order to understand, first in order to do the process analysis, what we need to do is, there are 5 processes are there. So 1, 2, 3, 4, 5. So first what you do is, you will have to see for this the entire process from the end to end process, you will have to map the process. We call that as a CPOC diagram. CPOC. So we will just see what is a CPOC program, CPOC in a few minutes from now. CPOC. So this is a supplier, input, process, output and customer. So how we are going to map that, we will see it in a short while from now. And then we'll have to do at a micro level what in each of these process, 5 processes, what we are doing at a micro level, that we'll have to clearly understand. So that we do it through process mapping. So we'll have to collect the data on at the micro level what is happening in each and every one of these processes. So we call that as process mapping. And then third one is the value stream mapping. So in value stream mapping, what we are trying to do is, we know that, okay, we have done the process mapping, and then while you are doing the process mapping, we are finding that, okay, there are some activities which are not really required, which are not really adding any value to the customer. So those type of activities we can identify and eliminate that. So that is what is value stream mapping. So we can do a value stream mapping so that we can simplify the processes and eliminate the wasteful activities so that your overall process efficiency can improve. So this is actually value stream mapping is a tool which will be helpful for you to improve your processes. And then we also have the XY diagram and FMEA. Failure mode and effect analysis. Okay, so now in the first session here, we are going to cover what all we are going to do as a part of the process analysis. So discover the different process definitions. So that means we are going to see what are the tools we are going to use for collecting the data so that we will be able to do a good process analysis, simplify the process so that the overall process efficiency can be improved. Then for the data analysis, again we need to collect a lot of data on transactions. Say for example, now for the same project, maybe now what you do is you collect the data for the last 6 months, then you collect what is the output, individual output for the machines for the last 5 months, last 6 months, then whether there was a problem in what are the data on the waiting time on the individual machineries, like that. You just collect a lot of data, and then this data you just first represent in graphical form, so that you will say, for example, now once you collect the data and put it in a graphical form, you may feel that, okay, the waiting time was more in just before the process 3. So that is what was causing a lot of delay in the overall supply. So this type of information we can get by collecting the lot of transactional data and putting it in graphical form. And then once you collect more and more data, then we can use more and more statistical tools for analyzing exactly what is the problems. So whatever the data we are going to collect for the data analysis, that we will cover as a part of the second session, that is explain Six Sigma statistics. And then in the third module, that is the third session, that is the perform measurement system analysis, what we are going to do is, whether we are just in each and every process we are collecting always how individual performance of the process is there, we are collecting some performance measures. Same way, like how you are talking about this on-time delivery, that is 85%. So again, this on-time delivery we are measuring. So we are also measuring this on-time delivery. So whatever the parameters we are measuring, whether the measurement system is right and consistent, so that the data whatever you are generating is right or wrong. So that type of analysis we do in the measurement system analysis. So why it is important is, say for example, why you have taken up this project now is that you are finding that on-time delivery is only 85%. So how did you arrive at? You have collected the data for the last 1 year, each and every month or each and every week, what was the on-time delivery, you have calculated the average and then found to be 85%. But suppose if there is a basic flaw in the calculating or in measuring the on-time delivery, then the entire project will be a failure because your baseline itself is not correct in that case. So in the perform measurement system analysis, what you do is we just see how we are measuring these individual performances, how we are measuring this particular process. So that needs to be checked. So there will be some manpower related elements will be there, there will be some method related element will be there, there will be measurement related issues will be there. So you will have to check all those things and ensure that whenever whatever you are measuring, you are able to measure consistently without any errors. So that is what we do it as a perform measurement system analysis. So in the last step, that is a calculate process capability, then now we have a sufficient data, and this data accuracy has also been measurement is also has been certified that yes, measurement system is right. Then using this, then we will be able to measure exactly what is our current level of performance. So we will have to baseline our current performance. So in order to baseline our current performance, we should know what is our process capability. Okay. So this is the step-by-step approach what we are going to follow during the measure phase. So that means, as I told you, in the measure phase, we are going to collect a lot of data which will be analyzed during the analyze phase to find out what are the root causes for the problems. So for the analysis phase, we need two types of data. One is the data for doing process analysis, and the second one is data for doing the data analysis. So for doing the collecting the data for process analysis, we have different tools, and for collecting the data on data analysis, we have different tools. And then we will have to ensure that all those measurements are correct. Then we do the measurement system analysis, and finally we do the process capability. So we will have to arrive at what is the current performance in terms of the sigma level. So this is what we are trying to do in the measure phase. So now first we talk about the process definition. So in the process definition, as I told you, we are going to learn some tools which will help you to go into the minute details of your processes, so that you will be able to identify the wasteful activities. Okay. So the first one is the cause and effect diagram, which is also called as a fishbone diagram. Then we will learn about the process mapping, SIPOC. There is a supplier, input, process, output, and customer. Then value stream mapping. So these are all some of the tools which will help you to break down your processes into sub-processes and activities to identify the wasteful activities. Then the XY diagrams, in order to find out which of the input parameters is having a major impact on the output parameter. So I will explain you when we are seeing this tool. Then finally the failure mode effect analysis. So these are the tools which will be helpful for you to collect data to do process analysis. Okay. Okay. First we talk about the cause and effect diagram. So this cause and effect diagram is also called as a fishbone diagram. Okay. So the different other names for these cause and effect diagrams are the fishbone diagrams, or we also call that as a 4M analysis. So nowadays we are talking about 5M analysis or 6M analysis, and we also call that as a Ishikawa diagram. So we call it in different names, but what we are trying to do is the same. So what we are trying to do is we are trying to identify what are going to be the causes for a particular effect. So for example, you have a problem. Okay, so this problem is a effect. And then for this problem, what are the different potential causes which will create this effect? So these causes can be either related to measurement, or related to material, or related to machine, or related to method, or related to manpower, or related to environment, or we call that as mother nature. So that is the reason why we call that also as a 6M analysis. So there are 6 M's. So we call that also as a 6M analysis. So this cause and effect diagram will help you to break down the problem into smaller pieces and then try to identify for this particular effect what are the potential causes. Okay. So at the end of doing this exercise, you will be able to clearly tell, yes, this is what is the problem, and for this problem, the possible measurement related issues are this, the possible material related issues are this, the possible machine related issues are this, the possible method related issues are this, the possible manpower related issues are this, and the possible environment related issues are this, so that you will be able to take some clear action. So now we will just see an example of a cause and effect diagram. Say for example, the problem identified as a part of your Six Sigma project is you want to reduce the turnaround time. So there is your turnaround time is very high. So in order to, you want to find out what are the potential reasons for this particular problem. So then this high turnaround time, this is the effect, and then you need to know for this effect what are the different potential causes. So what you do is you just do a brainstorming session. So I think most of you are aware about what is a brainstorming technique. You just call around 8 or 10 people who are involved in this process, and then you sit together in the presence of your moderator. So then try to generate as many ideas as possible, what are the potential causes, and then list down in this format what are the issues related to method, measurement, machine, material, mother nature and people. Okay, and then you get in this type of, normally you get around 30 to 40 potential causes for a particular effect. So this we call that as a cause and effect diagram or a fishbone diagram, which will help you to relate what are the potential causes which is creating a particular effect. So one of the very important tool what we use for the process analysis is the process model, or we call that also as a CIPAC diagram. So in this model, we can see that again any process, again the upstream process or the supplier is the one who is going to supply the inputs to this process. So this upstream process or the supplier, they supply the inputs, and then in the process again we have got some steps, and then the process will given some output, and which will go to either next process, which is a downstream process, or to the end customer. So this is what we call this a general process model. So in the first session when we are learning about the basics of Six Sigma, we learned that the process approach is the fundamental principle on which the Six Sigma methodology is built. So understanding the inputs and the process conditions is very, very important in order to find out what are the root causes for the problems in the outputs. So in the general process model, whatever you are seeing here, you can see that the raw materials, human resources or any services are the main inputs which are coming into the process, which are supplied by the suppliers or the upstream processes. So we need to have a tight control over the input measures, like the quality of the inputs being supplied to the process needs to be thoroughly checked. So if it is going to be a supplier from an external source, we have a process of doing an inward inspection to check whether the inputs are meeting the required specification. So if it is going to come from a previous upstream process, then again there is going to be some in-process inspection mechanism within the organization, which is going to ensure that the upstream processes are going to give the output which is required in the required quality level for the current process. So this input measures is an important step to ensure that the inputs are meeting the specifications as required by the process. And then once these inputs are supplied to the process, again we are having the process control mechanism, so that again each and every process conditions how it needs to be set up, and how it needs to be controlled. Everything is always described. So we will have to ensure that the process is produced in the under the controlled atmosphere as given in the process control. So that means all the conditions which are specified has to be strictly followed, so that the process is to be done under the controlled environment. And then whatever the process conditions are there, that needs also to be monitored. Like for example, a machine is running, then whether the speed is within the specification, whether the pressure, whether the temperature, if everything is in the set limits, that needs to be closely checked. And then after the output is produced, again we also need to check the outputs whether they are meeting the requirements. So these outputs, whatever you are producing from the process, has to meet the requirement for the downstream process or for the end customer. So the input measures, the process controls, the process measures, and the output measures are very important, so that we will be able to have a full control over the process. So this process model will clearly tell you how this can be controlled. So this is an example of a CIPAC diagram, as a very simple CIPAC diagram for a simple process. Say for example, we are considering making a photocopy as a process. Okay, so this process, the different inputs are there, like the copier, the machine, the paper, the toner, then the original document that needs to be photocopied, and the electricity. So for the different inputs, there are different suppliers. So the manufacturer of the copier machine again is a supplier for the machine. The office of the supply company, they give the paper and toner, so they are the suppliers for that. You want to take a photocopy of a particular document, so you are the person who is going to give the input for the original document. And then electricity is also needed, that is the input, and then the power company which is supplying the power will be again a supplier. So we have different inputs, and then there are different suppliers for the particular process. And then for this process again, it can be subdivided into some of the sub processes, like the first step will be to put the original on glass, then close lid, then adjust settings, then press start, and then remove originals and copies. So these are all the different steps that needs to be performed. And then for each of the step, under what conditions that need to be done has to be clearly defined as a part of the documentation, so that all the settings and the conditions has to be closely monitored, whether the process is happening on the in the right way. Then the output is the copies, and then again output also needs to be checked, whether the output is clear, whether there are no aberrations, all those things needs to be checked. And then finally the customers may be you, since you wanted the photocopy to be made, again you are the customer for that, and then the file in which it is going to go. So these are all some of the customers for this process. So for this simple process of photocopying, we knew that such a nice document can be made, CIPAC document, which is, so at a later stage, whenever you want to analyze what is the problem, why the Xerox copies are not coming correctly, then you can clearly identify whether there is a problem with the toner, or whether there is a problem in the copier machine itself, or the original itself was not very clear, or there was a fluctuation in the electricity which has caused that particular problem, or whether some of the process conditions were not followed properly, which has led to the problem. So this CIPAC diagram will clearly tell you the different inputs and the different process steps, so that you will be able to clearly identify what are the problems in the inputs and process conditions. So the advantages of using a CIPAC model are, the CIPAC model displays a cross-functional activities in a single simple diagram. So I have just given an example of a simple process like a CIPAC diagram, whereas for example a car manufacturing company can just give this CIPAC diagram for the car manufacturing process as a single CIPAC diagram. So here the processes may go for a cross-functional departments.
So different departments may be involved in that, and then even though different departments are involved, right from when the first part for the car is being assembled till the final delivery is made, whatever the processes are there, that can be simply deployed as a SIPAC diagram. So the SIPAC diagram displays a cross-functional activities in a single and simple diagram. And second one is a big picture perspective to which additional detail can be added. So once we have the basic information about the supplier, inputs, process and outputs and customer, then we can add more details into that so that it becomes more and more clear. Big picture we can get a big picture understanding. And it gives a framework which is applicable to both large and small organizations. So irrespective of whether that particular part is a very simple process or whether it is a complicated process, a SIPAC model can be made. So as I told you, a SIPAC model can be made for a photocopying process, or it can be made for a car manufacturing or car assembling process also. So that is the advantage of using a SIPAC diagram. So a SIPAC process model is designed to be a high level process view with 4 to 7 display steps. So it is actually a very high level document, so you can call that as a 50,000 foot level. So at that particular high level, so what is going to be who are going to be the suppliers, what are the inputs for that particular process, and what are the different process steps and the controls which are to be followed in the process, then the output and the customers for the process. So this is actually a very high level document which is having hardly 4 to 7 steps are explained here in this. Process mapping is a graphical display of steps, events and operations that constitute a process. So this is a pictorial illustration which identifies the steps, inputs and outputs and other related details of a process by providing a step-by-step picture of the process as is. So it is a graphical technique for dissecting a process by capturing and integrating the combined knowledge of all persons associated with the process. So actually whenever you are making a SIPAC diagram, it is very important that you make it along with the people who are actually doing the job, who will be able to give a very useful information while making the SIPAC diagram. So again, it is a team effort and it is documented by everyone who contributes to the process and are in the part of the process. So process map helps in characterizing the functional relationship between various inputs and outputs. So you will be able to clearly establish a relationship between the inputs and outputs by drawing the SIPAC diagram. So here we can see some of the process flow charts. So for defining the end-to-end process flow, there are different types of charts are available. The first one is the process flow chart. Again, this is a step-by-step approach from the start to end for a particular process. So with again we follow some sort of a standard shapes for depicting the process. Say for example, the oval shape indicate that it is a start and end of the process. The rectangles give that this is a process, and the diamond is used whenever a decision making point is arrived. So like that there are some conventions are being used while we make a process flow chart. So for a simple process of contacting another person over phone, this is a process flow chart. The first process, starting process is lift the receiver, then dial number, then again once you dial the number, ringtone will happen, and then you just see whether you are getting an answer or not. So if there are no answers, you just hang up. If there is an answer, say hello and then have the conversation, and after the conversation is completed, you just hang up. So this will give a process flow chart will give a step-by-step approach of all the activities that is being done in the process. So the next one is the deployment flow chart. So this is again similar to process flow chart, with the difference that here all the departments or the individual persons who are going to do that particular activity, they also will be represented in this particular diagram. Say in this example of placing an advertisement, initiating call, answer and review contract. So these are process flow. So here again it is the responsibility of the dealer to start the process with the place advertisement process, and then the call initiation will be done by the agent, and then the buyer will answer, then discuss, agree and hang up. So in this process flow we are also getting the person who is responsible for doing that activity. So that is also displayed here. So the next one is the alternate path flow chart, where we also have what are the different alternatives available, and then all those alternatives are also captured in this particular diagram. So here if you see, first process is decide whom to call, then look up the number, dial, and then once you dial, there are three different alternatives are possible, like if you are dialing and then if you are finding that nobody is answering, then you just hang up, that is one alternative. Or the second alternative is you just leave a voicemail message and then you can hang up. And then third alternative is if somebody is really saying hello to you, then you just continue with the conversation and then hang up. So for the same process, there are three different alternatives are there, and all those three alternatives are captured here in this particular format. So another very important tool which is used for the micro level definition of a process, we call that as a value stream mapping. So this value stream mapping is actually a very important tool which is used in the lean manufacturing or lean techniques, and for most of the lean projects they start with the value stream mapping. So in value stream mapping, what we are trying to do is we are trying to map the process as is using those process flow charts, and then try to identify or try to think of a process in future which is going to be a very efficient process. So again, then we try to compare what is the current process and what is the future desired process, and then whatever the gaps are there, how to bridge that gap. Again, we will have to prepare an action plan, and then we will have to implement those actions so that wasteful activities are eliminated. So the main idea of value stream mapping is to identify the wasteful activities in the process and eliminate them, so that we are doing only the value added activities in the process, and we are eliminating the non-value added or wasteful activities. So a value stream mapping is created to identify all of activities involved in product manufacturing from start to finish. This value stream may include suppliers, production operations, and the end of customers. So there are multiple benefits of a value stream mapping. So these are the step-by-step approach for doing the value stream mapping. So first thing, you will have to define the product family. So in your organization, you may be manufacturing different types of different families of the product. So you will have to first identify which product family you want to do the value stream mapping. So wherever you feel that the current processes are inefficient, where we are having a lot of wasteful activities, so that product family can be first identified as the area where we need to do the value stream mapping. Then once you have identified that particular product family, so for that product family, you try to draw the current state map. That means whatever the current processes are happening, you have to map it. And then for that process, you can imagine, and then you can just discuss with the people, brainstorm, and then see what is the future state map. That means you have to create a future state map, means what you really want to do, how efficiently you want to shape up the process. So that needs to be discussed, and then we capture that as a create future state map. And then once you have the both current as well as the future state map, then you can compare and then see, identify where are all the gaps are there. And then in order to bridge the gap, what are the different action needs to be taken, so that you again document as a implementation planning. And then for this, again you use a product equipment matrix, and then we'll have to do this personally using creative concepts. And then you can take months or years together for making the improvement. So it is not that you just do it once and then leave it like that. So this can be a continuous process. That means once you have created a future state map, then you have implemented the plan. So after maybe 3 months or 6 months, again you can review. So whatever the improved process can become the current process. And then from there, if you want to go to a higher level, then you can identify those actions, and then we can implement those plans. So like that, it can be a continuous improvement plan. So the first step is defining the product family. So the recommended value stream approach is to map one product family first. So wherever you are having the more problems, then that can be identified as the product family on which you can do the value stream mapping. So a product family can be defined as a group of products that pass through similar processing steps and over common equipment. So instead of doing the value stream mapping on different products, having different processes, using different machineries, then that will lead to a lot of confusion. So in order to avoid that, you can just select a particular product group which are going through the same processes and same equipments. So for this, again, a product and equipment matrix can be used to indicate the common features. So if you see, here we are having 5 different products, A, B, C, D, E, so which are having a clear set process flow, like product A is undergoing process 1, process 2, process 3 and process 4. So then the product A can be considered as a product group. Similarly, product B, product C, product D and product E also can be considered as a different product family. So whichever product is having the maximum problems, that can be taken up for value stream mapping. Okay, in some companies, since the processes can like extend up to multiple departments, then there may be a problem that a particular person who is doing the value stream mapping may not be able to get the right information from all the departments. So in order to take care of this problem, then in some companies, maybe a new position called a value stream mapper manager is created. So this manager will have an authority to make things happen, and he should report to the plant manager. So in that way, even if the particular process is going through the different departments, since that value stream manager is going to report to the plant manager, then he will have all the relevant informations for doing the effective value stream mapping. So these are the different critical steps of value stream mapping. So create current state mapping. So where a current state map of the process is developed to facilitate a process analysis. Then future state map, where a future value stream map is an attempt to make the process lean. And then the third one is the implementation plan. So this is to develop an implementation plan for establishing the future state by identifying the current gap between the current state and the future state. So these are all the different icons which are being used for during the value stream mapping, like FIFO, Kaizen burst, Kanban with tile, Kanban production, etc. So these are all some of the symbols which are used during the value stream mapping.
So next we move on to the next one, that is the XY diagram. So the XY diagram, what we are trying to do is, as I told you, whenever we are talking about the process analysis, what we told, we are trying to identify what are the input variables, input parameters which is going to have a output on the, which is going to have on the impact on the output variable. If you remember about that headache incidents, that situation, a boy was having a headache. So the output variable was the headache, and the input variables are the potential causes were the eye strain, the lack of sleep, infection, etc. So in XY diagram, what we are going to do is, we have identified all those potential causes. So these are the potential causes for the problem, and these are all the potential effects. Say here in this example, we have taken the welding, good welding, okay. The requirement is a good welding, and in order to get this good welding, so what are all the different input parameters which is going to have an impact on the welding parameter. So for that, first we will have to arrive at, if you are saying that it is good welding, then the welding need not be, it is not necessary that the quality of welding is assessed based on only one parameter. It can be gauged on multiple parameters. So that is why the output variables, that means whatever you are expecting, there are multiple factors are there. If you are saying that good welding means it should have a good weld strength, good appearance, there should not be any pinholes, and then the flexibility should be there. So these are all the different output characteristics needed for a good welding. And then depending upon their importance, again we are giving a rating in the scale 1 to 10. So since here for this particular project we are focusing more on weld strength, then for this particular output parameter we are giving the maximum rating of 10. Then for the other parameters, depending upon their importance, then you are giving the ratings at 8, 7, 4 like that. So this weightage is given depending upon the importance of this output parameter for your project. Since your project is focusing on how to improve the weld strength, so you are giving the maximum rating for weld strength, and for the others you are giving a relative grading. Then what you will have to do is, you will have to list down all those input parameters which are input and process parameters which are having the influence on the welding. So now we have identified the ultrasonic weld frequency, power amplitude, initial gap, contact pressure, dwell time, hold time. Okay, so these are all the different potential causes for which is having the impact on the welding. So now what you will have to do is, you will have to again do some sort of you will have to again collect a team and then do a brainstorming session, and then try to identify what is going to be the impact on each and every input parameters on each and every output parameter. So for example, what is going to be the impact of the ultrasonic weld frequency on weld strength? Then what is going to be the effect of this ultrasonic weld frequency on weld appearance? Then what is going to be the impact of ultrasonic weld frequency on pinhole density? Then what is going to be the impact of ultrasonic weld frequency on weld flexibility? Again you will have to give a rating of 1 to 10. 10 if it is going to have a very high impact, and 1 if it is going to have a very low impact. So this team has given this rating of 8, 4, 7, 5 for each of these output parameters. Now in order to get this overall ranking, what we need to do is, we need to multiply this is 10 into 8 plus 8 into 4 plus 7 into 7 plus 4 into 5. Okay, so that is 80 plus 32 plus 49 plus 20. So adding all this you get 181. So like that you just do for each and every what is going to be the impact of each and every input parameter on all those output parameters, you get these ratings, and then you just do the similar exercise and get the individual rating. Then what you can do is, you can just arrange all those causes in a descending order, so that you will be able to know which one is having more impact. So normally what happens is, whenever you are trying to map the inputs and outputs, you find that there may be some around 30 to 40 inputs can be identified, which is going to have an impact on the output parameters. This XY diagram will help you to identify and prioritize the inputs. So that is the main use of using the XY diagram. This will prioritize the inputs on which data can be collected. So for example, in the measure phase you will have to collect the data both on the outputs and inputs side, and then whenever we did the first brainstorming session, then we identified them some 30-40 possible causes are there. Is it possible for you to collect the data on all the 30-40 causes? No. So that is the reason why we have to do this XY diagram, so that we will have to identify the top say 10 or 15 causes. So once by doing the XY diagram, you just identify the top 10 or 15 causes, so that on these 10 or 15 causes we can collect the data. So that is, we are trying to narrow down the causes, so that we will be able to do we will be able to collect the data. Okay. So if you really see what is happening in Six Sigma project, so whenever we are trying to identify the reason, first you start with brainstorming session. So you start with brainstorming session, you identify some 30-40 reasons, then you do the XY diagram, then you narrow down to 10 or 15, then you do some statistical tools, so narrow down to 3 or 5,
then make some another test. So you'll be able to find out some 2 or 3 potential causes. So this 2 or 3 again you just try to control, then you will be able to, because these 2 or 3 will be the most important causes which are having the greatest impact on your output. Then this you identify the problems, solve the problems, then you will be able to consistently get the consistent output. So this is how you do the Six Sigma project. And then we started off with the brainstorming session, identify all the potential causes. Then we did this XY diagram, and then we narrow down this 10 to 15, and then we start the data collection on this 10 or 15 inputs, and then this data will be used for the analyze phase. I think I hope you are very clear about what we are trying to do. Next, we learn about the tool, about this FMEA. So the FMEA is actually failure mode and effect analysis. So we'll try to understand what is FMEA. So it is a step-by-step approach for identifying all possible failure modes in a design, a manufacturing or assembly process, or a product or service, their causes and the effects as perceived by the end user. So FMEA is an effective tool which will be able to identify the problems before a particular design is made, or before a process is being done in a manufacturing or assembly process, or before a product is produced, so that we will be able to take some proactive actions to prevent errors. So that is the purpose of doing a FMEA. So whenever a design can fail because of various reasons, a process can fail because of various reasons, the product can fail because of various reasons. So if after completing the design, or after completing the process, or after making the final product, if that defect is identified, then there will be a huge loss. So for example, assume that currently aeroplane engine design is there, and the company wanted to go for building a more fuel efficient engine, which will help it to improve its operating profits. So while doing that, again, assume that they have made some changes, design changes, which has really given a improved fuel efficiency. So now, can the company go ahead and then directly implement the improved design? No, because even though this particular change in design has helped them to reduce the operation cost by improving the fuel efficiency, we do not know whether, with respect to the quality or safety, whether some other parameter has been compromised. So if that particular problem has happened, and then because of the change in design, either a quality feature or a safety feature has been compromised, then the losses will be huge, and then the reputation of the company also may be in stake. So that is the reason, before even the design is changed, before even the manufacturing of the engines as per the revised designs are taken up, then we need to do a FMEA to check what are all the possible ways in which the design can go wrong. So whether a particular safety feature has been compromised, whether a particular quality feature has been compromised. So once we start identifying these failure modes, then we can analyze what could have been the possible causes, what will be the effect of it, and then how can we build in some detection mechanism so that such failures can be detected at an earlier stage. Then we will be able to make those improvements in the design stage itself, and then again we will recheck. So this has to be done continually till we are very confident that that change in the design has not really affected any other parameters adversely, and then we will be able to confidently implement that change. So the purpose of failure mode effect analysis is to make any changes to the design or process or the product, so that any possible failures are discussed before even the design or the manufacturing or the product production is implemented, so that proactive actions can be taken to improve. So first we need to understand for FMEA what is the relationship between the failure, cause and effect. So a failure mode can be caused by so many reasons and it can result in a particular effect. So I will just explain this FMEA through a example. So I am a trainer and I am offering training services to some of the training institutes, and then the services what the quality of service what I am offering to these institutes can be gauged from the fact that whether I am able to give an uninterrupted services of training without any interruption. So that means on a particular day, if I have to provide 8 hours online training to my the participants, then I will have to see whether I have the capability. Then I will have to do a analysis of what are the different ways in which the failure can happen in the services whatever I am doing. So I will use this case study while I am explaining you this concept of FMEA. So first we try to understand the different terms. So a failure mode is the way in which a specific process input fails. So what are the different ways in which the particular product or service or a design can fail? So that is the definition of a failure mode. So the effect means, so once the failure mode has happened, then what will be the impact on the failure on the CTQ, on the critical quality parameter. So if that particular failure mode has happened, then what will be its effect? So that is the effect. So cause is, what is the cause or what are the sources of variations that has resulted in the failure mode. So that is the cause. Current controls means what are the current systems and procedures or equipments which are available in place to prevent or detect the failure. So current controls means whether currently we are having the processes and devices in place to identify the failure modes. Then the severity, occurrence and detection ratings are given with a scale from 1 to 10. 1 for the severity, the rating is 1 if it is not having a severe impact, and 10 if it is going to have a very severe impact. So from 1 to 10, what is the criteria for giving the any rating in between these values? Again, we will have a table at the end of this session. Similarly, for frequency, occurrence, again the frequency with which a cause occurs. So again, it has to be rated in the scale 1 to 10. Then detection, ability of the current control to detect the cause before creating a failure mode. So how easily we will be able to detect the failure mode. If it is very easy to detect, then we will give a rating of 1. If it is very difficult to detect it before the failure happens, then we give a rating of 10. So these are the different definitions or terminologies you should be aware before we proceed to learn about FMEA. So failure mode, effect, cause, current controls, severity, occurrence and detection. So FMEA can be used in 3 different ways. The first one is the design FMEA. So a design FMEA is done to identify and eliminate failures during the product design itself, considering all types of failures during the entire lifespan of the product. So whenever we are designing the product, and then before launching, you will have to make a thorough analysis as to whether that particular design will be robust, will have all the safety features, will meet all the extreme conditions. All those things needs to be thoroughly analyzed before the design is new design is released or any design changes are being done. So we call that as a design FMEA. Any FMEA done at the design stage, we call that as a design FMEA. Same way, process FMEA is focused on failures of processor of how the product is manufactured, maintained or operated. So what are all the different ways in which a process can fail? So that is being analyzed, and then proactive actions can be taken by using the process FMEA. Same way, system FMEA will look for the failures and bottlenecks in larger processes such as the entire production lines or systems. Say, for example, in a entire car assembly in a car manufacturing company can be taken as a system, and then we can do a system FMEA to really see what are the possible failure modes, and then we can take some proactive action. So this is actually a step-by-step approach for doing the FMEA. So first review the current process, so or review the current design. Either we have to review the current process or the current design, and then we have to brainstorm what are the potential failure modes. So in what way the particular design or the product can fail. So we'll have to list down all the potential effects of failure. So once you have listed all the potential effects of the failure, then we'll have to assign the severity rating. So from the scale 1 to 10. Then how frequently this failure can happen. So based on the frequency, again we'll have to assign the occurrence ranking. And then using the current control, then how easily we can detect these failure modes. If it is easy to detect it, we give a rating of 1. If it is very difficult to detect it using the current controls, we give a rating of 10. Then we'll have to calculate the RPN. So RPN is the risk priority number. So risk priority number, and this we calculate by using the formula. RPN is risk priority number, and this is calculating by multiplying the severity into occurrence into detections. So whatever the rating we are given in the scale 1 to 10, so we'll have to multiply these 3 ratings in order to get the risk priority number. So once we have calculated the RPN, then we'll have to develop the action plan. So again, on what failure modes we need to take action, again will be left to the person who is really doing the FMEA template. So for example, the maximum rating for a failure mode is 10 into 10 into 10. This is the maximum scaling, this is 1000. And the minimum RPN that is possible is 1 into 1 into 1, that is 1. So whenever you are identifying the failure modes and then calculating the RPN, so the RPN will lie somewhere between 1 to 1000. So now the person or the department who is doing the FMEA can take their decision on which of those failure mode they need to take some action. So some of the organization may decide that okay, I will take action on the top 5 RPN failure modes. Some of the organization may decide that wherever the RPN is more than say 500, then on those failure modes I will take action. Some organization may feel that okay, I will take action wherever the severity is 7 or more. Or some of the organizations may take that okay, wherever the frequency is more than 8, I will take action. So on which failure modes we are going to take actions, that will depend upon the department or the person who is doing the FMEA. Then based on that priority, then we will have to prepare an action plan. So once we have prepared the action plan, then we will have to implement the action plan and take actions. And then we will have to, after we have implemented the action plan, again we will have to recalculate the revised RPN. So if our action has been effective, then there will be a drastic reduction of the RPN of the failure modes. So then no need for us to stop only with that. Then what we can do is we can again do a FMEA study after the 3 months and then try to identify more and more failure modes. So FMEA can be done on a continuous basis. So that is why it is not that FMEA needs to be done only during the measure phase or analyze phase or improvement phase of a Six Sigma project. So FMEA can be done during any phases of a Six Sigma project. It is a continual improvement activity. So this is a template on which the FMEA can be, the results can be recorded. So the first one, the first column says it is a name or function, so which process we are doing the FMEA, and then what is the potential failure mode, and then what is the potential effect of the failure, and then what are the potential causes of failure, then what is the current process controls in place, what are the current what is the reduction rating, what is the occurrence rating, and what is the severity rating. And then once you have these 3 rating, then what is the RPN. So once you know RPN, then if this is going to be a very high RPN, then what is the recommended action for in order to reduce the RPN, and then who is responsible for it and when you need to complete the action. So after the action has been completed, again you will have to recalculate the RPN and see whether there is a reduction in the RPN. So if there is a reduction in RPN, that means this particular problem is not a important problem, prioritized problem, and then we can look for some other important problem to be solved. So I will just give an example of I will just do a small FMEA on my training process on the, so that you will be able to clearly understand how it is done. So the process I am trying to do, this is the online training. So online training is the process. So the potential failure mode is that there is a the interruption in training. So potential effect of the failure. So I will not be one of the potential failure is the way my training is going to be affected is the power failure. Okay. So my online training can be stopped, interrupted because of the power failure. So what will be the impact if the power fails? Then since I do not have a power backup, then the severity will be 9 or 10 we can say, because I will be able to take up the training only because as soon as the power goes off, then my internet also goes off, and then I will have a backup only for the laptop. So since it will be immediately affected, then I give a rating of 10. So the effect is going to be 10. Then how often this power failure happens, because this power failure is a potential failure mode. So then in Chennai, the power normally goes off not very frequently, but I can give a rating of around 7. The scale of 1 to 10, I can give a rating of 7. Then what is the current control mechanism, so that whether I get a warning, pre-warning before the power goes off. So here the power suddenly goes off without any warning. So it is very difficult for me to detect it before the power failure happens. So I give a rating of 8. So the RPN, if you calculate, then 10 into 7 into 8, that is 560. So that means this is a very high RPN. So there is always a great risk of my training being affected because of the power failure. So now the recommended action is that I go for a UPS, uninterrupted power supply. So if I go for an UPS, then I will be able to protect both the internet connectivity as well as I will have the power backup for at least 8 hours. So then immediately then I just went for a UPS in order to have the power backup both for the laptop and for the internet connectivity. And then after the action is taken, so the action taken is the UPS. So after the UPS was taken, then the severity has become only 1, because now for 8 hours I will be able to give uninterrupted training even though power fails, since I have the power backup. And then this has not really made any changes in the occurrence of power failure, because that has not changed. So that will remain 7, and the current detection also is remaining same, because whatever the action I have taken UPS, that is going to have an impact only on the severity, not on the occurrence and detection, because that again depends upon the current the supplier who is supplying the power to us. So now the revised RPN is 56. So just by taking a proactive action, so I have been taking this online training for the last 2 years, but never ever I have failed in my training, offering the online training services just because of power failure. Because as soon as I came to know that I have to start taking the online classes, immediately I analyzed the potential problems, and then I had invested on the UPS. Okay, so this has helped me to avoid any problems at a later stage. Same way, once this is solved, then I can just see what is the next failure mode. So next failure mode can be internet connectivity. So again internet connectivity. So again internet connectivity, again the potential effect is again 10, because again when the internet goes off, again I will not be able to connect to the participant. Again current the occurrence, again that is around 7, because some of the service providers, there is a frequently there is a failure in the services. And the detection, I don't get any warning, suddenly it goes up, so that is also 8. Maybe I can give 7. So 5, 6. So this 490. So again this is also a very high RPN number. So again for this, the corrective version I took was that I went for a data card from a different supplier, different service provider. So once I went for a data card for a different service provider, then again, even though there is a disruption in the internet because of a particular service provider, I will be able to continue the training with getting the connectivity from the data card which is given by some other different service provider. So again, this has become 1, 7 and 7, so 49. So the FMEA will help you to take some proactive actions before the failure happens. So the RPN, or the risk priority number, is calculated by multiplying the severity, occurrence and detection. So this is used to prioritize the concerns and actions. The greater the value of RPN, the greater is the concern. So the RPN ranges from 1 to 1000. So the team must take efforts to reduce higher RPNs through corrective action. General guideline is over 100, you will have to take some actions. So this is actually a guideline for how you are going to give the rating from 1 to 10. So for severity, you give a rating of 1 if there is no effect. If there is and for occurrence, you give a rating of 1 if the occurrence is very remote. That means the failure is very unlikely, less than 1 in 15 lakhs or 1.5 million. And detectability, so design control will detect the potential cause or the mechanism. That means even before the failure happens, the current control will easily detect it. Then you give a rating of 1. Similarly, you just go off. So if you for the rating of 10, that means it's a very high severity rating when a potential failure mode affects operation without warning. That means the entire design or the entire process fails without any warning. Then we will have to give a rating of 10. Sometimes we also say that whenever there is going to be a fatal, the effect is going to result in some fatal fatality, then we can give a rating of 10. Occurrence, again failure is almost inevitable, almost 1 in 2. Then again detectability 10, whenever the current control will not be able to detect the failure and the failure happens without any warning. Okay, in that way FMEA will help you to take some proactive actions before the failure happens. So in this session, we have learnt about the cause and effect diagram or a fishbone diagram. We also learned about the process mapping, CyPack diagram and value stream mapping. We also learned about the XY diagram and also the failure mode and effect analysis. So those are the different tools which will help you to do the process analysis during the Six Sigma project, so that the process wasteful activities in the process can be identified and eliminated, and the potential causes for problems can be identified, and this can be taken up to the analyze phase for analyzing.
So in this session we are going to cover the Six Sigma statistics. So by the end of this session you will be able to define basic statistics, explain descriptive statistics, describe normal distribution and normality, and illustrate different graphical analysis. So in the last session we discussed about the data to be collected for doing the process analysis and the data analysis. So in the last session, we covered all the tools which are required for collecting the data for the process analysis. So in this session, we will cover all the tools which are going to be used for collecting the data for data analysis. So before going into this, we'll have to have a fundamental understanding of some of the terms in statistics. So first we will start with the definition of the term data. Since we have been talking about the data for so many time, and then for the Six Sigma is a data-based approach, so the understanding of the data and the data type is very, very important. So data is nothing but an organized information. Say for example, as a green belt, you are collecting the data on the on-time delivery performance. Then you are having, say for example, the number of the months in one column, January, February, March, April, May, up to December. So for 12 months you are collecting the data. So the months are in one column and your performance, that is the percentage on-time delivery, is in the other column. So now since you are collecting this number, that is a percentage on-time delivery for each month, and then you are presenting that, then we call that as a data, because this is a organized information, right? So from that you are able to infer something. Once you know that, okay, it has been, whether it is fluctuating or whether it is increasing or decreasing, so that it will give a information to you how the process is performing. So that's why we call data is an organized information. So there is a misconception that data should be always be in numbers. So many times whenever we talk about data, only the numbers come into everybody's mind. But data need not be only numbers. It can be like words, measurements, observations, etc. also. So the example whatever I gave you, if you are going to talk about in the data, we are going to talk about, as I told you earlier, is the month and percentage on-time delivery, percentage OTD. So January, February, March, April, May, etc. And here you have 85%, 90%, 92%, like this. So we are collecting the data like this. So this is also a data. So here you see that this we call that as this is a number. So this is a numerical data, and this is the description. There's no numbers here, but still we call that as a data. So that's why I told you that data means it need not be only numbers, it can be in other forms also. So only thing is, once a combination of the data we have got some organized information is there. So the data can be broadly classified into two categories. One is the quantitative data or the numeric data, and another one is the qualitative data, or we call it as a attribute data. And again, in the quantitative data or the numerical data, we have got two divisions. The first one is the discrete data, and second one is the continuous data. Whereas for the qualitative data, we have the categorical, ordinal and nominal. So the understanding of the data type is very, very important. So as we are going to progress through the measure phase and analyze phase, we will come across many instances where the importance of the understanding the data type becomes very, very important for you. Because whatever the tool you are going to use for analysis or for improvement will be purely based on the what type of data we are going to have. Already you know about X and Y. X are the input variables or the causes, and Y are the output variables or the effects. So whenever you are going to collect the data on X's and Y's, depending upon the data type of X and the data type of Y, the type of tool which you are going to use for analysis or for improvement will be different. So that is the main reason why a clear understanding of the data type is very, very important. And even like whenever in the control phase, you are going to plot some control charts, again, which type of control chart you are going to use for controlling the process will also depend upon what is going to be the type of data you are going to have, whether it is qualitative or quantitative. So you will have to listen to this with very careful attention need to be given for this. So this is what I had shown you in the previous slide. So the discrete data, so the first two are the quantitative or numerical data. So these two are numeric data. So in the numerical data we have two types, one is the discrete data and another is the continuous data. So here we say discrete data can only take on a unique set of values. So that means these are all discrete numbers. So one of the easier way of remembering the discrete data is an outcome of whenever the outcome of the process can be counted, outcome of counting process. Outcome of counting process, we call that as a discrete data. So for example, I am just collecting the data on the number of boys in each class in a school. So for example, class 1, there are 50 people. Class 2, there are 60 people. Class 3, there are 65 people. Then this 50, 60, 65, we call that as a discrete data, because these are all like unique values, and then this is an outcome of a counting process. So we call that as a discrete data. Then again, the other type of numerical data is the continuous data, which can take on any value on a continuous scale, such as temperature, distance, cycle time or profit. So here again the clue what I can give you is any continuous data is an outcome of a measurement, as a measurement process, measuring process. So what does it mean? Say suppose if you measure the time, right? If you measure the distance, you measure the temperature, you measure the pressure, you measure the height, so weight, so height, weight, pressure, temperature, etc. Whichever all time, whichever can be measured, we call that as a continuous data. Why we are calling this as a continuous data is, in the discrete data we find that between 50 and 60, like only some, the 50 is discrete and the 60 is unique, right? But suppose if I give you a data, if I ask you like how many number of data points are there between 61.1 and 70.1, suppose if you say that the weight of two different people are 61.1 and 70.1, right? So this is actually the weight of two different people. So if I ask you like how many data points can be there between these two data points, 61.1 and 70.1, then there can be infinite data points will be there, right? Infinite data points. Because this is between 61.1 and 70.1, maybe the 65.73333 like that, 67.723 like that, there will be a lot of, so infinite number of data points will be there between any two data points. So that we call that as a continuous data, and you can remember that a continuous data is an outcome of a measurement process. Then in attribute data, that means it is qualitative in nature, so we will not be having any numbers. And then there are three types of the attribute data or the qualitative data. Attribute data, there are three types. The first one is the binary data, where is a categorical type of data made up of dual classification. So whenever we are having the data in the form yes or no, pass or fail, on or off, male, female, whenever you have got only two options, then we call that as a binary data, 0, 1, many times you say that 0, 1, pass, fail, yes or no. So those type of data we call that as a binary data. So nominal data is a type of data that is descriptive with more than two categories. For example, names. So suppose I am collecting the data on the name of the person and the telephone numbers. Name, and the telephone numbers. Then whatever the data we are going to get, we call that as a nominal data, because here we are having the description. Then the third one is the ordinal data. So again, this also can be equated to the discrete data. It can also be take the any numerical values, but only the difference here is, here the unique data means there is no connection between relationship between these two numbers, whereas for the ordinal data, whereas for the ordinal data, you have a, say for example, whenever you are doing a market survey, and then you are taking some feedback, and then you are asking the participants to rate the performance in the scale 1 to 5, and then say that 1 means poor and 5 is excellent, and then people will give their values in as 1, 2, 3 or 4 depending on where they are feeling. So here whatever the rating they are going to give, they may give 1 or 2 or 3 or 4, but again whenever they are giving the number, then it has got a meaning to it, right? That means 1 means it is poor and 5 means it is excellent. So such type of data where the information is organized in a particular order without indicating the specific relationship between the items, we call that as the ordinal data. So you can just remember that ordinal data, whatever the data you are using for survey, we can call that as the ordinal data. Whenever you are getting the rating or the grading, we call that as a ordinal data. Okay, so now we are slowly entering into the statistics, which is the core subject to be learned for the Six Sigma projects. So before going into the details of the statistics, I would like first to start with a small exercise with you. Say for example, you assume that there is a selection team is there who are interested with the job of selecting the a team for the World Football 11 team, who are going to play with the world champions. Okay, so in that now there are 3 people who are competing for the 2 positions for the forward position, right? Suppose Messi is there and Ronaldo is there, and okay, we consider there are 2 participants are there, Messi and Ronaldo, who are competing for 1 position. So now the selectors say that they will select the person who is the better player and who is a consistent player. Means they are going to check who is the better player and who is the consistent player based on the number of goals they have scored over the last 10 matches. Okay, in the last 10 matches, whatever the goals they have scored, based on that data, whatever we are going to collect, who is going to be the better player and who is going to be the consistent player, he will be selected for the team. So now if you take the data for Messi and for Ronaldo, if Messi has scored the first game, he has scored say no goals, in the second he has scored 1, in the third he has got 3, fourth one 0, fifth one 1, sixth one 0, 0, and then 1, and then 1, and then 0. So these are the number of goals scored by Messi in the last 10 matches. And then for Ronaldo, again the same data stands at 2, 1, 2, 1, 1, 2, 1, 1, 1, 2, and 1. So if this is going to be the data collected for the last 10 matches, then how will you select who is going to be the better player? So in order to see who is the better player, then what we do, we just calculate what is the average score by both the people. Whoever is having the better average is the better player. So if you calculate the average for this, then for Messi it is 4, 5, 7, that is 0.7, and for Ronaldo it is 3, 4, 5, 7, 8, 9, 10, 12, 13, that is 1.3. So since the average number of scores scored by Ronaldo is 1.3, which is better than the average number of scores scored by Messi is 0.7, then we can call Ronaldo as the better player because he has on an average he has scored more goals when compared to Messi. Same way, in order to find out who is a consistent player, we have to find out what is the standard deviation. We will learn about it in a short while to go, but I'll just want my information. And then whoever is having the standard deviation as a lesser, then he is a consistent person, because if standard deviation is less, that means the variability is very less. So for example, we are getting a standard deviation as 1 here, and if you are going to have the standard deviation as 1 here and 0.8 here, then again Ronaldo is the more consistent player because his standard deviation is less, right? So in that case, since the selection team has decided that they will select the better and consistent player, then they will select Ronaldo because he has got the better average and lower standard deviation. So from this example, what we are coming to know, initially we had the data, right? We had a set of numbers. But when we had the set of numbers, then we were not able to infer anything from that numbers. We were unable to come to a conclusion whether Messi was a better player or Ronaldo was a better player, whether Messi was a consistent player or a Ronaldo was a consistent player, right? Even though we had 20 data points were there, we were unable to come to any conclusion. But when we calculated some arithmetic values, like we made some calculations, and then after doing the calculations, we found out what was the average and what was the standard deviation. And once we had those numbers, then these numbers, with these numbers, we were able to come to some conclusion. So this is what we call that as statistics. So that means we had the data. So if you see, we had the data, and then we made some arithmetic calculations by calculating the mean and the standard deviation. So to the data, we did some calculations, we did some arithmetic, and then the output we get was the statistics, right? This average and the standard deviations are statistics. So once we had these statistical values, then we were able to make some decisions. So that is what we call it as a statistics. So statistics is nothing but data plus arithmetic. So we are collecting the data, and whatever the data we are collecting, we are doing some mathematical calculations, and based on the mathematical calculations of the data, whatever the outcome we are getting, that is statistics. And if the data is reliable, then the decisions whatever you are going to take from the statistical testing will be more accurate. But it is just like garbage in, garbage out. If the data is inaccurate, then the decisions we are taking based on the statistical calculations will also be wrong. So that is why the reliability of data is very, very important. And as a green belts, since you are all going to be involved in the data collection, you will have to really understand why the reliability of data is very, very important. Because all the data, whatever you are going to collect, is going to be used in statistical tools. And if the data is not accurate, then the results, whatever you are going to get, also will not be correct, and you will not be able to come to any conclusions. So, in statistics, there are 3 branches of statistics which are helpful for us in our Six Sigma methodology. The first one is the descriptive statistics. So we will just see what is in short while from now, that is the descriptive statistics, and second is the inferential statistics, and third one is the probability theory. So statistics has got many branches, but whatever is going to be useful to Six Sigma methodology, we are having three major fields, that is the descriptive statistics, inferential statistics, and probability theory. So first we will have a look at what is descriptive statistics. So here in this example, whatever I have done is a example of is a descriptive statistics. So that means given a collection of numbers, if there are some meaningful ways to summarize the information contained in the collection using one or two summary values. So here we had originally some data points were there, 20 data points were there, but when we were able to calculate some summary values like average or standard deviation, then we were able to have some meaningful information. So this is what we call it as a descriptive statistics. So whenever from the data we are collected data, we are trying to find summary values, then that type of activity we call that as a descriptive statistics. And then the other aspect of descriptive statistics is also representing in graphical representing in graphical format. So whatever the data we are collecting, whenever we are going to represent them in graphical format, we again call that as a descriptive statistics. So descriptive statistics, there are two main actions whatever you are doing. One is collection of summary values, and second one is representing in pictorial or graphical format. The next one is the next branch of statistics which is useful to us is the probability theory. So what do you mean by probability theory? Given a known universe, what can we say about samples drawn from this universe? Say for example, you have a pack of cards. So in a pack of cards we have 52 cards, right? So now out of these 52 cards, you just draw one card and then you just keep it face down, and then you are trying to predict what is that particular card. Okay. Suppose now you are taking out one card and then try to see what is the probability of that card being a king. Okay. So then you know that the total population here is 52. So the population is total number of cards which was available was 52, right? So out of the population of 52 cards, how many kings are there? There are 4 kings, right? In 52 cards, there are 4 kings. There is spade, clubs, diamond and hearts. There are 4 kings are there, right? So if out of 52 cards you are just selecting one card, then what is the probability of that card being a king? So that is equal to the total number of kings in the card, in the pack, divided by the total number of cards. So that is equal to, this is the probability of a card being the king. So the total number of kings is 4 and the total number of cards is 52. So the probability of a card being king is 1 by 13. So what is the probability of the king being a heart king? What is the probability of that card being a heart king? So again, that is equal to the total number of heart kings divided by the total number of cards, that is equal to 1 by 52. So whenever you know everything about the universe, that means you know whenever you are doing collecting some data, whenever you have the information about the whole population, but you do not know what is the sample, how the samples will behave, then we use the probability theory. Okay. So we know the universe, but we do not know about the samples. So from the knowledge of the population, we are trying to predict what will be the behavior of the sample. Then we use the probability theory. The next branch of statistics which is going to be useful to us is the inferential statistics. So here this is actually a opposite of the probability theory. So in probability theory, we knew about the population, but we do not know about the samples. But in inferential statistics, we do not know about the universe or the population, but we know everything about the sample. So that means it is entirely the reverse of the probability theory. So in inferential statistics, we do not know about the population, but we know everything about the sample. And from the knowledge about the samples, we are trying to predict what is going to be the population. And then we call that as a inferential statistics. So this inferential statistics is mainly used for one of the classical example where inferential statistics is used is the opinion polls, right? Or the exit polls. So what is happening here? Say suppose by-election is happening in one of the constituency in India, where assume that there are 7 lakh voters are there. So now a newspaper, they wants to predict before the election who is going to win. So what they will do, because it is not possible for you to collect the opinion from all the 7 lakh voters. So what they will do, they will just take around 10,000 samples from these 7 lakhs, and then they will get the voting preference from these 10,000 people, and from the results of whatever they are getting, they will try to predict who is going to win. So that means here the population is 7 lakhs, this is the population, and the sample is 10,000, and they know everything about the results of the sample, and then knowing the results of the sample, they are trying to predict what is going to be the result of the population. So this is what we call it as a inferential statistics. Okay. So in order that the results are very accurate, we need to ensure that the samples are homogeneous. So what do you mean by the samples are homogeneous? So that means we will have to determine what are the factors which will have the impact on the voting pattern. So it may be like the sex of the voter, whether it is male or female, then their salary groups, then caste or religion or something like that. So you list down what are all the prominent factors which decide the voting factor, and then this ratio of in the samples, this the distribution of the say, so for example, the in the population, you know that 50% are male and 50% are the female. Then in the sample also, you should collect from 50%, means out of these 10,000, 5,000 should be females and 5,000 should be males. So like that, the distribution of these factors should match with the distribution in the population. Then only the samples will be called as homogeneous. If you are going to collect all the 10,000 opinion from males, and then you don't take any opinion from the females, then whatever the result you are going to get is not going to be accurate. So that's what we are saying it in the next slide. We call that as a homogeneity. So we have to ensure that the data, whatever we are going to use, should be homogeneous. So it is very important to know whatever we have covered in the last 4 slides. So there are 3 branches of statistics which are helpful to us in Six Sigma. The first one is the descriptive statistics, where we are collecting the data and calculating some summary values, and from the summary values you are getting some useful information, and also we are representing the data in graphical format, that is descriptive statistics. The second one is the probability theory, where we know everything about the population. We do not know how the samples are going to behave, and using the knowledge of the population, we are trying to predict what is going to be the behavior of the sample. We call that as a probability theory, and we had the example of trying to predict card which has been drawn from a pack of 52 cards. And the third one is the inferential statistics, where we know everything, we do not know anything about the population, but we know everything about the sample which has been drawn from the population, and based on the results of the samples, we are trying to predict about the nature of the population. We call that as a inferential statistics, and we saw that exit polls or opinion polls is an example for the inferential statistics. And in all these 3 statistics, we will have to ensure that the data is homogeneous. If the data is not accurate, then whatever the results we are going to get using the statistical tools is not going to be right. Okay? Okay, now let us see how the data can be classified. So the data can be classified into 4 types. The first one is the nominal, the second one is the ordinal, third one is the interval, and fourth one is the ratio. So you can see that nominal, again you have seen in the last slide,
The nominal means again it is descriptive. So for example, if you want to collect the data on the color preference of the different customers of a car, then the red, gold, silver, and green. So these are the different colors. So color can be one of the nominal data. Same way you want to collect the data on the revenue for different locations. Then you can say that okay, northern region, eastern region, western region, southern region. So like that, again that can be a nominal data. So the nominal scales distinguish one item from another, but they do not rank or quantify data. You can just say that okay, these four northern region is different, southern region is different, western is different, and eastern is different. Only the difference can be shown, but we cannot be able to find out the quantify between the different types. So we call that as a nominal data. So the nominal values should be mutually exclusive and can be exhaustive. So sometimes suppose if you want to collect the data on the population of all major cities in India, and you have identified 100 cities, then these 100 cities will become the part of the nominal data. So it can be it should be mutually exclusive, and it can be exhaustive also. Then the next type of data is ordinal. So in ordinal scales, we actually group the different data into magnitudes depending upon the relative magnitude. So for example, you can categorize the people into low income, medium income, and high income, and the customer satisfaction, you can ask them to rank in the scale from 1 to 5, where 1 is poor and 5 is excellent. So these are all we can just give examples for ordinal data. So here the difference between 1, 2 and 3, 4 and 5 does not have any meaning. We know that 1 means poor and 5 means excellent. 1 is bad and 5 is good. But we cannot really quantify what is the difference between 1 and 2. How better is 1 when compared to 2? That we do not know. It's only a comparison of ranking, and we will not be able to quantify that. So in ordinal data type, we are just ranking, and then the ranking cannot be quantified. It's only can differentiate the different levels, but we cannot cannot quantify the differences. So in interval, here the scales include the average values and densities. So for example, we are measuring the temperature, and one place we are measuring 20 degrees centigrade, and another place we are measuring as 40 degrees centigrade. So it does not mean that the place which is having 40 degrees centigrade is twice as hot when compared to 20 degrees centigrade. It is only an interval. So that means we are measuring the temperature in an interval from say minus 20 to say plus 50 degrees centigrade, and then this is the reading we are getting. So the readings can take any value between minus 20 and 50, but we do not have any, we cannot just say that okay, a place which is having 10 degree Celsius as a temperature is 10 times hotter than 1 degree centigrade. So that type of quantification we cannot do. So that is the interval data. And the last one is the ratio, where we are talking about some absolute measurements on a continuous or discrete phenomena. So here, suppose if I say that in a bigger auditorium there are 1,000 people, and in a smaller auditorium there are 500 people, then we can clearly tell that the number of people in the bigger auditorium is twice as high when compared to the smaller auditorium. So here we will be able to quantify in terms of the ratio. So same way, like any blood pressure we are measuring, and then whatever we are measuring, we are able to say that this is so many times higher than that. If you are able to connect to that, then we can call that as a ratio. So we need to really understand in which of those four categories a particular data is falling.
Okay, so these are all some of these inferences from the descriptive statistics. As I told you, we are going to collect some summary values like the measure of central tendency, measure of dispersion, probability density function, frequency distribution, and cumulative distributive function. So these are all some of the summary values we are going to calculate as a part of descriptive statistics. So measure of central tendency. So how will you? So again, this measure of central tendency is one of the summary values, whatever you are trying to calculate in descriptive statistics, summary values. Say for example, suppose if you have in your project, you have collected the data like this, say 1, 3, 5, 7, 9, 11, 13. Okay, so this is the data points you are getting. Then how do you calculate the mean? So for calculating the mean, what you do is you add all those individual numbers and then divide it by the total number of data points available. So here you just add all these numbers, you get 4, 4 plus 5, 9, 16, 25, 36, 49. So the mean will be equal to 49 divided by the total number of data points is 7. So the mean is equal to 49 by 7, that is equal to 7, right? Then how do you calculate the median? In order to calculate the median, first you will have to arrange all the data points in ascending or descending order, and then whatever is the middle number we get, that is the median. So here in these data points, again we are already arranged that in the ascending order, and if you are selecting the middle number, then we are calculating, we are finding that the median is 7. So suppose instead of 7 numbers, you are going to get 8 numbers. If you are going to have an even number of data points, then we'll have to select the middle 2 points and then we'll have to calculate the average of these 2 middle points. That's how we calculate the median. Then what is mode? Mode is the most frequently, which occurs most frequently. So suppose here we cannot calculate the mode because all those data points are repeating only once. But suppose in some data points where if you are having a particular number is appearing more number of time, then that will be the mode. So this mean, median and mode are the 3 summary values we calculate as a part of the descriptive statistics. And mostly the mean is the normally used as the measure for central tendency, and median is sometimes used for in the statistical purpose. Mode is very rarely used. Next we see how we are going to calculate the measures of dispersion. So there are these 3 are the main summary values we are calculating as a part of measuring the dispersion. So the first one is the range, quartile deviation, mean deviation and standard deviation. So depending upon for which data we are going to calculate those measure of dispersion. If it is for population, for mean we call that as mu. If it is a sample, we call that as a x bar. Same way for standard deviation, if you are calculating for population, then it is sigma. If you are calculating for sample, it is s. If you are calculating the variance for population, we call that as sigma square, and if it is for sample, we call that as a s square. Okay, now we will just see how we are going to calculate the measures of the dispersion for some of the data points. Okay. So suppose again I just give suppose my data points say that it is again the same data points I am giving 1, 3, 5, 7, 9, 11, 13. Okay, so these are the data points you are having. So how do you calculate the range? So the range is the difference between the largest and smallest values, that is L minus S. So for this data point, L is the least, that is 1 is the least data point, and the lowest, that is the smallest is 1 and the largest is 13. So range is equal to 13 minus 1, that is equal to 12. That is the range. Then how do you calculate the quartile deviation? It is the half of the difference between first and third quartiles. So how do you calculate the first quartile? We call that as Q1, and third quartile we call this Q3. So how do you calculate Q1 and Q3? So suppose if you are having the 7 data points, so whatever we are having in the middle value, we call that as a median. We call median also as Q2. And then now the data points are being divided into 2 distinct points, and then again you calculate the median for this one and the median for the bigger one. Then this is called as Q1 and this is called as Q3. So if you see the quartile deviation, QD is equal to, what is Q3 minus Q1 divided by 2, that is equal to 11 minus 3 divided by 2, that is equal to 4. So this is how we calculate the quartile deviation. Then standard deviation is a formula is there. You would have learnt in the higher standard mathematics, that is equal to root of x1 minus x bar whole square, like that it will go on. So you can calculate the standard deviation using that formula. And we also have one more variant, we call that as a variance, that is equal to standard deviation whole square. So mean deviation is normally not often used, so not necessary for you to have a look at this. So range, quartile deviation, standard deviation and variance. So mostly standard deviation is the most commonly used measure for dispersion, and in some cases we use a range and in some cases we use a variance. So now I think you have learnt about the measure of center tendency, that is the mean, median and mode, and measures for dispersion, that is the range, standard deviation and variance. How to calculate? Now we have a clear understanding.
Okay, now let us see the comparative status of the different types of measures for central tendency, like what are the advantages of using the mean or median or mode for one another. So the advantages of using mean is that it considers every data point. So that means whenever, suppose you are for a particular problem, you are collecting one data set containing say 50 data points, then while calculating the mean, all the 50 data points are used, because you know that the formula is you have to calculate the sum of all the data points divided by the total number of data points. So each and every data point is used for calculating the mean, and then even if one data is getting changed, then the mean value will change, so that it is considered to be the more accurate value of the measure for central tendency when compared to the median and mode. And then it is also possesses a very nice mathematical and statistical properties. So whenever we talk about the normal distribution and then normality and all during the later part of this course material, then we always find that mean is the most frequently used measure for central tendency, because it gives a very nice mathematical and statistical properties. So if you are able to know what is the mean and the standard deviation of the population, then we will be able to predict its behavior. In that way, mean is a very popular and most often used measure for central tendency, especially for the normal data points, normal data sets. But the disadvantage of using the mean is that it's affected by extreme values. So for example, you have an outlier in your data points and you are not sure whether that data is really a genuine data or whether it is because of some mistake by somebody, and you are not in a position to eliminate the data, then in that case this will affect the overall calculation of the mean. Say for example, you are measuring some pressure values and then you are getting 2.1, 2.3 like that, and suddenly you are getting around say 8.2. So then whenever you want to calculate the mean, then this will have a very great impact on the mean. So at that point of time you will not be really knowing whether to, or it will be very difficult for you to decide whether you want to keep the data or whether you want to remove the data from your data points. And other disadvantage with the mean is that it is very tedious to compute. So since you are have to take the square of the deviation from the mean values for each of those data points and then add everything, and then you have to take the square root, then this becomes a tedious method for calculating the mean. So until unless you have some sort of a software or a computer, it is very difficult for you to calculate the mean. So these are the main disadvantages of the mean. That means affected by the extreme values. And the second thing is it is tedious to complete. And third one is for the open-ended class intervals, like you will not be able to compute the mean. For the median, we also call that as a positional average. You know that if the data are arranged in ascending or descending order, the middle point is called as the median. And then it is not affected by the extreme values. So here we are just saying that out of this, say we are having say 50 data points. So out of these 50 data points, whichever is going to occupy the middle two, that is the 25th or 26th data points, these are all going to have affect the median value. So even if there are going to be some extreme values in the lower side or on the upper side, it is not going to have an impact on the median. So median can be effectively used as a measure of central tendency for the data sets which is having some outliers or extreme values. And then the other advantage is that it can be computed for open-ended class intervals, and then it can also be used for qualitative data. Like for example, you are having some attribute data, then you will be able to use median for measuring the central tendency. So the disadvantage is that it employs more complex statistical procedures. So at a later stage, whenever you are going to learn about the more complex statistical tools, then mean is preferred as a preferred measure for central tendency rather than median, because in those tools, if you are going to use median, that will involve a lot of complex statistical calculations. So that is a disadvantage of using the median. And then the mode, again the advantage is that it is not affected by the extreme values, and it can also be used for qualitative data. And the disadvantage is that it is difficult to interpret and compute in case of multimodals. So suppose in a data you are getting say 4 or 5 numbers as a mode, because like for example mode is nothing but the most frequently occurring data set. So in a particular data set, if some 3 or 4 modes are coming, then which one is the real mode, or which is a real measure for central tendency, we are not sure. So that is the reason why mode is not preferred quite often.
Okay. Now we need to know about the normal distribution, which is a very important aspect as far as the Six Sigma is concerned. So if you really see what is the normal distribution, say for example, assume that in a class of in an auditorium there are about 100 adult Indian males have assembled. 100 adult Indian males have assembled. And then we want to predict what is going to be the range in height of all these 100 people. Is it possible for us to predict? Yes, it is possible, because you find that an average adult Indian, the height will be between say 5 feet to 6 feet, or if you calculate in terms of centimeters, it may be minimum may be 150 and maximum may be say 185. Okay, centimeters, if you calculate in centimeters. So how do you arrive at this fact, this 150 and 185? It is based on, because we know that over the last for so many years we have collected the data and we found that there is a pattern. So we find that there is a pattern in the height of the Indian adult males, and then whenever we take some random samples and then we try to find out, we find that the range will always be within this. So this is because the height of the Indian males are normally distributed. So what is meant by normally distributed? So that's what we are going to see now. So I think most of you would have seen in the curve like this. So this is actually whenever a population is normally distributed, we just represent it in this form. We call this as a bell curve or a normal distribution curve. And then we see that here we find that most of this, the peak is somewhere in the middle. We call that as a mean. And then the distribution is like coming down on both the sides. So if you see the characteristics of normal distribution, it will look like a, we call that as a bell curve. And then we find that the tails are asymptotic. So what do you mean by asymptotic? That means it is not touching the x-axis. It is just running parallel to the x-axis. So that's why this both the tails will not touch the x-axis at all. It will meet only at the infinity. That's why we call that as asymptotic. And then curves can be divided into equal half with pieces falling either side. So you can say that it is equally distributed both on the left and right side. And the most frequently occurring value, that is the mean, is at the center. Then the area under the curve, total area under the curve is 1, and a normal curve indicates a random or chance variation. So that means if you are collecting the data and we are saying that it is normally distributed, so that means the process is running only because of the chance variations or the common cause variations. The common cause variations can also be called as a chance variation or a random variation. So that means the process is running only under the influence of common cause variation, and there are no special cause variations in that. Okay, so we will learn more about it in the analysis phase. Okay, so the peak of the curve represents the center of the process. Then normal distributions are divided into 3 standard deviations on each side of the mean. So suppose we represent mean as mu and standard deviation as sigma. Then we find that on both the sides we have, this is minus sigma, minus 2 sigma and minus 3 sigma. Same way this is plus sigma, plus 2 sigma and 3 sigma. So that means the entire curve can be accommodated within plus minus 3 sigma. So this is actually a property of normal distribution. Okay, so now we find that the normal distribution is characterized by mean and standard deviation. So whenever we have a population and whenever we know what is the mean and what is the standard deviation, then we will be able to immediately tell about the process. So a normal distribution is characterized by the mean. This is the mean and this is the standard deviation. So this plus minus 3 sigma will be accommodating the 100% of the values. Okay, so here many times we find that, say for example, now your company is manufacturing pens. Then the diameter of the pens, the specification of the pen is that it should meet 10 plus minus 0.5 millimeters. So in this case, the LSL, that is the lower specification limit. Lower specification limit, LSL, is 9.5 and USL is the upper specification limit, that is equal to 10.5. So this is what is the lower upper specification limit and lower specification limit. So now we have seen that 100% of the data point, and then assume that for this production process the mean is equal to 10 and sigma is equal to 0.1. So that means 100% of the data points will lie between 10 plus minus 3 into sigma, that is equal to 10 plus minus 0.3, that is between 9.7 to 10.3. So that means this point will be 9.7 and this will be 10.3. So that means this process or the machine which is producing these pens will always be able to meet the requirements of the customer, because the machine will always produce the pens with outer diameter between 9.7 to 10.3, whereas the customer is willing to accept from 9.5 to 10.5. But suppose if there is a problem in the machine and then the variation in the variation is increased and sigma has become 0.2. Then in the revised case, what will happen? Mu is equal to 10 and sigma is equal to 0.2. In that case, then the distribution will be somewhere like this. So now what happens? The specification limit remains the same because the customer has not revised the specification, but your the output will become 10 plus minus 3 into 0.2. That is equal to 10 plus minus 0.6. That is 9.4 to 10.6. So that means this becomes 10.6 and this becomes 9.4. So whereas the customer is going to accept only up to 10.5. So that means whatever you are going to produce less than 9.5 and whatever you are going to produce more than 10.5, these are all going to be rejections. Okay. So this again we will learn more about it whenever you are calculating the process capability. So this is actually very important to know at this point of time, because whenever you are going to calculate the process capability, then you will find whatever the learnings you have got today is going to be very useful to you. So you have to understand is that whenever you know the mean and the standard deviation, then we will be able to predict what will be the total spread of the entire population. That means the 100% of the data will be lying between the mu plus minus 3 sigma. So that is the learning you will have to have at this point of time. And then another important aspect here is, as I told you, almost 100%. That is not 100%, it is exactly 99.73% of the data points will be lying between. So if you see this is a mu, we have considered as 0. Then we have considered sigma is equal to 1 here. So that is the reason. So this is actually 3 sigma and this is minus 3 sigma. So we find that almost 99.73% of the lies between plus minus 3 sigma. 95% of the data points lie between plus minus 2 sigma. And 68% of the data points lie between plus minus sigma. So this is a very important concept that you need to understand. So that means whenever a population is distributed, 68% of the data point will be lying between plus minus sigma. 95% of the data points will be lying between plus minus 2 sigma. And 99.73% will be lying between plus minus 3 sigma. Okay. So in the earlier session, you learnt about the how descriptive statistics is helping in finding the summary values and thereby characteristics in a particular data set by calculating the summary values like the central tendency like mean, median or mode, or the measure of dispersion like standard deviation or variance, etc. So we also learned that the other aspect of the descriptive statistics is representing the data in graphical format. So there are different graphical formats which are available and which will help you to really represent the data in graphical form so that the problems or the observations become very clear. So instead of seeing some 2 or 3 sets of data in numbers may not really give you any information, but you represent that in a pictorial format, say example like a box plot or in a histogram, then you will be able to clearly visualize whether this is coming from 2 different machines or 2 different shapes, or whether the variation is less or more. Just by seeing the picture you will be able to make out. So that is the use of using the graphical analysis. So the graphical analysis includes the tools like box plots, stem and leaf plots, scatter diagrams, run charts, histograms and normal probability graphs. So now in this session, let us try to understand how to draw the box plot, stem and leaf plot, scatter diagram, run charts and histogram using, and then these are the some of the graphical formats which you can derive from softwares like Minitab.
So here in this slide you can see some of those graphical formats. The first one is the histogram, the second one is the run chart, and third one is a probability, normal probability graph. Okay, first let us learn about the box plot. So the box plot will help us to find out how the central tendency, spread, skewness, and the existence of outliers. So the box plot is plotted in such a way that you are getting a box in the middle, and you are having a whisker on the top and whisker on the bottom, and then you are having some points outside. Okay, so the box, the bottommost part of the box, that is the 25th percentile, or we can call that as a Q1. I think you have learned it whenever we learned about the measures for dispersion. So Q1 is nothing but the 25th percentile point. So, and then this top of the box is the Q3 or 75th percentile point. And this Q3 minus Q1 is the interquartile range. So that is the length of the box will show you, give an idea about the interquartile range. And then the central line which is there inside the box, that is actually the median or Q2. So here the box, studying the box will clearly tell you how the median is located, whether it is exactly located at the center. If it is exactly located at the center, then means the population is more normally distributed. There is no is not skewed. But suppose if you see below the mean there are a lot of data, and above the mean there is only less data is there. That means this particular distribution is negatively skewed. Okay, since we are seeing a lot of data points below the mean, we are having a lot of data points. So this is a negatively skewed distribution. So we will be able to get an idea about what is the where the central is lying, where the center point is lying, and then how about the spread, how the variation is there, and about the skewness, whether it is negatively skewed and positively skewed. And also we get an idea whether there are any outliers. So a box plot is a set of summary measures of the distribution of the data. So here again the whiskers will go to a length of either 1.5 times IQR, 1.5 times IQR, or lower extreme value, whichever is lower. Say for example, if 1.5 IQR is going more than the below the lower value, then we stop with the lower value. Same way, the upper point, we go up to 1.5 into IQR, but if 1.5 IQR is more than the upper value in the data set, then we stop the whisker with the upper extreme value. So the end of the whiskers are either the lower or upper values as per the data set, or 1.5 times IQR, whichever is lower. And the points above the or below the whiskers, we call that as an outlier. So box plot will clearly give an idea about where the center is lying, then whether the distribution is positively skewed or negatively skewed, or what is the extent of variation in the data set, and then whether there are any outliers. So here again we are seeing an example where we have 3 data points, and then we have the corresponding box plot. So just by seeing this 3 data points, we can say that the mean or the central tendency for data set 2 is higher when compared to the other 2. And then variability for 3 is the least. You can see that the variability for data set 3 is the least, because we are saying that the box size is also small and the whiskers are also small when compared to the 1 and 2. 1 and 2 we are having more variation when compared to the population number 3. and we are saying that okay, out of these three data sets there are no outliers. So just by seeing these three box plots, instead of seeing the data, we are not inferring any useful information, but by seeing the box plot, we will be able to clearly identify in which population the central tendency is higher and where the variation is more, and there are any outliers. So here, if there are any outliers are there, then these outliers needs to be investigated in analyze phase. And here in population 1 and 2, wide variation is there. So we need to really understand what are the reasons for these variations during the analyze phase. So next we start with the histograms. So a histogram is a graphical method for displaying the shape of a distribution. So we have earlier learnt about the normal distribution, where we are supposed to get a uniform, that means equal halves on the below and above the mean. So this is actually the normal distribution. So in normal distribution, in both the sides, both on left and right, we are having the equal value. But in reality, this may not happen, and then different, we may be able to get a different shapes. So this bell-shaped one, we call that as a ideal normal distribution, but again, which may not be happening on the in a practical situation. So in practically, you may get a double peaked. We also call that as bimodal. So when we get a bimodal distribution, it may suggest that maybe the data is coming from, say, two different operators or two different machines or two different batches of material, etc. So there is clearly a variation between two data sets. So if the same data is represented in number, maybe we will not be able to differentiate the data. But if you are representing in the histogram pattern, then clearly it will come out and say that there are two distinct data sets are there. That is the advantage of using the histogram. And then here, again, we call that as a negatively, positively skewed, since more data points are there in the past. Similarly, we can get a negatively skewed population also. Then here, we are getting a truncated one. So that means maybe this may represent a situation where we are doing a 100% inspection, and whatever the parts which are in the negative side of the tolerance, maybe that has been inspected and has been eliminated from the population. So that's why you are getting a population like this. So any truncated shape might have been a result of doing a 100% inspection. And sometimes you may also get a ragged Plato sort of thing, where there is no single clear process or pattern. So this may be happening because maybe the process is not in control. So again, the histogram again is also help to find out whether there are any outliers are there. So if any outliers are there present in a histogram, then you cannot blindly ignore this, remove this data. We'll have to really analyze whether this data is significant, and we'll have to analyze the reasons for getting this type of outliers in the data sets. Okay, so whenever we are drawing a histogram, there are two important properties of the histogram we need to know. One is about the skewness, and the other is about what we call it as a kurtosis. So the skewness will tell you, the middle one we call it as a bell-shaped curve. So that is what is ideally for the ideal normal data set. But many times you can also get a skew to the right or skew to the left. So whenever we find more data points at the right side of the mean, we call that as a skew to the right. And whenever we see more data points to the left side of the mean, we call that as skew to left. Okay. Same way for kurtosis. Again, ideally, the bell curve should be sharp, and it should be like it should neither be flat nor too sharp. But suppose if you are having some population where it is very sharp and the tails are very narrow, we call that as a leptokurtic. And if we are the peak is very flat and the shape is very wide, then we call this a platic kurtic. So these are all the different skewness and kurtosis we get it in the normal population.
So if skewness is positive, then the data are positively skewed or skewed to right, meaning that the right tail of the distribution is longer than the left. So whenever you are plotting a histogram and you are finding that the skewness is having a positive value, so that means the population is positively skewed. Same way, if the skewness value you are getting in the negative, then that means the data is negatively skewed, meaning that the left tail is more longer. If skewness is equal to 0, that means the data are perfectly symmetrical. But in a real world situation, this is more unlikely. So if the skewness is less than -1 or greater than 1, we call that distribution is highly skewed. If skewness is between -1 and -half or between +half and +1, then we call that as a moderately skewed. If skewness is between -half and +half, then the distribution is approximately symmetric. So these skewness values will give an idea about how far the data set is skewed. Skewness is very high or very low. Similarly, we are whenever we are talking about the kurtosis value, a normal distribution has kurtosis exactly 3. So any distribution with kurtosis approximately or nearer to 3, we call that as mesokurtic. Any distribution with kurtosis value less than 3, we call that as a platykurtic. So that means compared to a normal distribution, its tails are shorter and thinner, and often its central peak is lower and broader. So that means you can see more of a flat sort of distribution. So that's why we call it as a platykurtic. That means it's almost like a plateau, means longer and shorter. A distribution with kurtosis greater than 3, we call it as a leptokurtic. So compared to your normal distribution, its tails are longer and fatter, and often its central peak is higher and sharper. So that means when the height is more and the tails are shorter, we call that as a leptokurtic. So for negatively skewed population, again the mode is in the middle, median is next, and then mean is the lowest. So for negatively skewed population, this is the position of the mean, median and mode. And for the normal distribution, perfectly normal distributed, all the 3, mean, median, mode, all the 3 will be exactly at the center. And for the positively skewed, the mode is on the left side, median is next, and then mean is to the next. So that is for the positively skewed. So the understanding of the position of the various measures for central tendency is very, very important. So a special table, next we will learn about the stem and leaf plot. So this is a special table where each data type is split into a stem, the first digit or digits, and a leaf. So example, suppose if you are having the data set, this is the data sets we are having. So between 10 and 20 we are having 15 and 16. So here both the cases the 10th digit is 1. So then in the stem we are representing the 10th digit, and then the leaf we are just saying the unit digits. So in the stem 1 and leaf 5 means it is 15, stem 1 and leaf 6 means it is 16. Same way between 20 and 30 we are having 22 and 28, so we are representing that as 2 and 28 here. Same way 3 to 34, 35, 36, 38 can be represented here. So a stem and leaf diagram will immediately tell you where most of the data is lying. So here immediately by seeing the stem and leaf, you will be able to clearly tell that between 30 and 40 we are having more number of values. So that is how the stem and leaf plot is useful to us. Then we learn about the scatter plot. So a scatter diagram is a graphical display of many XY coordinate data points which represent the relationship between two different variables. It is also referred to as a correlation chart. So if you really want to find out whether there is a relationship between two variables x and y, then we should go for a scatter diagram. So whenever you are plotting two variables, so x and y, and then if there is going to be if there is a positive relationship between these two variables, then we will get a increasing straight line. So if you are getting an increasing straight line, that means
we are having a strong positive correlation between these two variables. So as x is increasing, if y is reducing, then we call that as a strong negative correlation. If there is no straight line relationship is there, then we call that as no correlation. Here you can see that there is no specific pattern is there, increasing or decreasing pattern is there. So we call that between x and y there is no correlation. So if instead of a very sharp line we are getting a more flatter lines, then maybe the relationship is there, but it is not very strong. So that is why we call that whenever we are having a increasing but the lines are not so sharp, we call that as a possible positive correlation. And whenever we are getting a not a sharp line but a decreasing trend, we call that as a possible negative correlation. And then sometimes we also get a curvilinear pattern where the relationship may be a curvilinear. So plotting a scatter diagram will tell you whether there is any linear relationship between two variables, or there are no relationship between these two variables, or there are curvilinear relationship between these two variables. So it is very important to know that previously we have learned that always we are talking about y and x, where y is the output variable and x is the input variable, right? So here, just because I have written x and y here, it doesn't mean that whatever I have written here is the input variable and whatever I have written as y is the output variable. So this is not the case. So this x and y are random. That means a scatter plot will not tell you which is the input variable and which is the output variable. A scatter plot will always tell you whether there is a relationship between two variables. It will not tell you whether it is a output variable or input variable. And that knowledge of whether it is an input variable or output variable has to come from the process knowledge. Okay, then we move on to the next graphical format, which we call that as a run chart or a trend chart. So a run chart will give you how a particular process is running with respect to time. So many times what happens is as we go on in time, then there may be the process either may be stable and then continue to produce the consistent quality output, or sometimes there may be a deterioration in the property. Either it may show a increasing trend or a decreasing trend. So a run chart is actually a plot in which the whatever the metrics you want to measure, that is being measured in the y-axis against the time and the x-axis. So with respect to time, how the measured variable is behaving, whether it is showing a random behavior or whether it is showing some patterns. So that's what a run chart will help you. So if a process is running under the influence of only common causes and no special cause variations are there, then the points should be uniformly distributed above and below the middle line. So if you are getting the individual points, if they are randomly distributed above and below the middle line, then we can infer that the process is stable or process in control. So, but if there are going to be any patterns are there, so that means it is, so in this case when the process is stable or control, that means the process is running under the influence of only common cause variations. That means when there are no visible patterns in the run chart and when the individual points are distributed above and below the middle line equally, then we call that the process is stable or the process is in control. That means the process is running only under the influence of common cause variation. Whereas in the run chart, if you are seeing some patterns, like here you can see that some consecutive points are having the same value. In some other plots it may be like continuously increasing or continuously reducing. So this type of patterns indicate that there is a special cause variation in the process. So a run chart will help you to identify whether the process is running under the influence of only common cause variations or special cause variations are also there in the process. So whenever you are trying to improve your process and you are collecting the data, you should ensure that the data should be collected only when the process is running under the influence of common cause variation, or the process is stable, or the process is in control. If the process is not in control, then you will have to identify the factors which are contributing to that particular trend, eliminate those causes, and then again recheck the run chart. Only when the process is running, the process is stable and running under the influence of only common cause variation, then only you should collect the data, and then you will be able to start any improvement activities. So it is very, very critical to plot the run chart of any process first before even we start thinking about improving it. So there are different type of run charts which are available depending upon the pattern whichever we are showing. So if in a particular you are plotting a run chart and you are finding that some 7 or more points are having the same value, we call that it is a same value plot, and then this indicates that there is a bias in the process. Same way, if we find that here we also have another pattern, we call that as a clustering plot. So here a lot of data points next to each other on one side of the median and the same way on the side of the median over time, and indicates a periodic shift in process average due to lot to lot or setup variability. So that means either we can say that there is a lot to lot difference is there, or between setup there is a problem is there, and that is the reason why there is a shift in the process. We call that as a clustering plot. We also call that as a too few runs plot. So what do you mean by too few runs plot? So whenever the middle value is crossing from here to here, whenever it is crossing the middle line, we call that as a run. Same way, here again it is crossing the middle line, so we call that as a run. Same way, here it is crossing the median, we call that as a run. So here if you are going to if you count the total number of points, it is going to be 5 plus 6 11 plus 5 16 plus 6 22. So there are totally 23 points are there, but we have only 4 runs are there. So that is why we call it as a too few runs plot. So that means there is sort of a clustering which is happening, indicating that there is a lot to lot or a set of variabilities there in the process. So this is a special cause variation. Okay, next one is a mixture plot. So here we do not have any points nearer to the central line, and we say that a sequence of 14 or more points in a row alternating up and down. Here you can see that the alternate points are moving up and down. So again there is a pattern, and here you can see that contrary to the previous one, here there are 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 runs are there, whereas for a total points of 6 8 10 12 14 16 18 20 22 23. So there are only 23 data points are there, but for these 23 data points there are 17 runs are there. So that is why we also call it as a cycle plot or too many runs plot. So in a mixer plot or the cycle plot or a too many runs plot, here we are saying that there is a systematic variation between the individual points. So the individual points are alternating up and down. So this indicates a bias or systematic sampling from different sources or processes. So the next one is a oscillation plot. So here the data points are constantly fluctuating up and down rapidly around the median and indicate that the process is not steady or stable. So here you can see that the points are rapidly varying up and down. So next one is a trend chart. So in a trend chart, if you are having 7 or more consecutive points either increasing or 7 or more points continuously reducing, we call that as a trend plot. So if 7 or more points are continuously increasing or continuously decreasing, that means there is a shift in the process, and that needs to be immediately identified and arrested. Then shift plot, whenever we are having a sequence of 8 or more points on the same side of the median, then that indicates a gradual shift in the process. So we call that as a shift plot. So in this session, we have learnt about the basic statistics, the descriptive statistics, the normal distribution and normality, and the different graphical analysis.
So in this session, we are going to learn about how we are going to define the precision and accuracy. So in this session, we are going to learn about the measurement system analysis. So as I had explained to you in the earlier sessions, during the measure phase, it is very important that whatever the measurement system we are having has to be validated, that whatever the readings it is giving is okay. If our measurement system is wrong and we are collecting the data from that measurement system, then the reality may not be really coming into picture. So that is the reason we have to ensure that the measurement system is right. So in order to do that, we do the measurement system analysis. So by the end of the sessions, we will be able to define the precision and accuracy, describe bias, linearity and stability, explain the gauge, repeatability and reproducibility, and recognize the variable and attribute MSA. So by the end of the session, you will be able to define precision and accuracy, describe bias, linearity and stability, explain gauge, repeatability and reproducibility, recognize variable and attribute MSA. A measurement system analysis is a specially designed experiment that seeks to identify the components of variations in the measurement. An MSA is done to verify that the measurement system produces valid data. So this is done before taking any database decision. The MSA is also known as gauge, R&R or gauge. R&R here means, so here R&R gauge GRR means gauge, repeatability and reproducibility. So it is an experimental and mathematical method of determining to what extent the variation within the measurement process contributes to the overall process variability. So depending upon the data type, the statistical analysis will be different. So you see that I have already explained that variability in a process is inevitable, right? So any process, whatever you are doing, whether it is manufacturing or whether it is marketing or whether it is finance, any process, the variability is inevitable. So if you see, measurement is also a process. Again, there may be a lot of variations caused because of the measurement, right? So because whenever we are measuring, what are the different components which are involved while we are measuring? Again, we are measuring using the people. So variations can come because of the people. We are using different measuring instruments. So variations can come because of the instruments. Different people may measure it in different manner. So the method can contribute to some variation. And then again, the environmental factors like temperature or pressure, etc. So this also may have lead to some variation. So suppose you assume that the particular measurement you are taking, assume that you are measuring the diameter of a rod, okay? So its original diameter is 10 mm. you are measuring the another rod, its original diameter is 11 mm, right? So there is a difference of 1 millimeter between these two. This is the actual diameter of these two rods, 10 mm and 11 mm. This is actual. But suppose, because by some mistake you are measuring this 10 as 10.1 and this 11 as 12.1, then what happens is the measured values. So here the actual difference between these two readings is only 1 millimeter, but you are measuring and you are reporting as if there is a difference of 2 millimeter between these two rods. So that means the original difference is only 1 millimeter, whereas your measured difference is 2 millimeter. So that means your measurement is variation is up to 50%. So in that case, you find that the original difference is as good as the measured variation. So your measurement is adding to the variations in the process. So that is the reason why we need to do the measurement system analysis, and then we will have to take proper steps so that the variations because of the people or instruments or methods are minimized, so that the aim of doing the measurement system analysis is to minimize the measurement variations. And so that whenever you are measuring much of the variations is coming because of the process variation rather than the measurement variation. So here we have seen, suppose if there is going to be a overall variation in a particular measurement, a particular process, then the variations can come either from the process or from the measurement. So why the variations is coming in the measurement? Because there may be, even within the instrument, there can be a variation. Between instruments, whenever you are making the same measurement in different instruments, again variation can come. Between calibrations, so suppose if you are calibrating the instruments every 1 year, so during the time just the calibration is completed and during the time when the calibration is due, then there may be some variations can come between the calibrations. Between operators, so operator to operator, variations will come, and across time. So these are all some of the elements which are contributing to the measurement variations. Same way for the process variations, again within unit, between units, between lots, between operators, between machines, between setups, and across time. So these are all the factors which are contributing to the process variation. So the purpose of doing the measurement system analysis is to reduce the measurement variation so that the overall percentage of the measurement variation is very less when compared to the total process variation. So when we talk about the measurement system, we need to be clearly understand what is accuracy and what is precision. Okay. First we just see the measurement system accuracy. Say for example, I will give you an example. Let us see that you are just making some measurements in a weighing machine. Okay. So now assume that you are weighing a 20 kilogram standard weight. So when we talk about this 20 kilogram standard weight, this actually the standard weight is calibrated to internationally traceable standard. Okay. So even if you are measuring at any weighing machine anywhere in the world, it should show the same 20 kg, right? So what happens is, now you just take this 20 kg standard weight and then take it to a weighing machine and weigh it 20 times. Okay. 20 readings you are going to get. So do you think that every time for all the 20 times you are going to get exactly the value as 20 kg? No, it's not possible. Say you may get the values like say 19.98, 20.03, 19.95. So like this you will get different values. Even the same standard weight you are weighing in the same machine, but you are taking 20 readings. All the 20 readings or most of the 20 readings will be different, right? So what you do is you take the average of all the 20 readings. So the average of 20 readings may come to say 19.95, right? So the difference between the here the 20 kg is the expected value. This is the expected value, and this 19.95 is the average of actual values. So the difference between these two, we call that as accuracy or bias, right? So if you see here the definition of the word bias, it is the difference between average measured value and a reference value. So in the example I have given, the average measured value is 19.95 and the reference value is 20 kg. Okay, so the difference between these two, that is 0.05, is the bias or accuracy. Okay, so normally if you are finding there is any difference is there, any bias is there, or if there is any problem with respect to the accuracy, the corrective action normally we take is the calibration, because once you do the calibration, then we will be able to get the expected values. So if you want to measure the accuracy or bias, what we do is we just take a standard or a expected value and then measure that, get the average of the actual values, and then find out the difference. The difference will be the bias or the accuracy. Now we just get accomplished to the other terminologies related to accuracy. So the first one is the linearity. So the linearity is used to examine the accuracy of a gauge. Linearity examines how accurate your measurements are through the expected range of the measurements. So for example, again taking the case of that weighing machine, so I explained to you the term bias using by weighing a 20 kg standard, right? But suppose if the machine has a capability of measuring from say 1 kg to 100 kg, what we have to do is, again you just do the accuracy or bias measurement using a 1 kg standard, using a 10 kg standard, using a 50 kg standard, using a 100 kg standard. So that means the standard should be taken throughout the entire product, throughout the capability of the particular machine, the operating range, because the machine can weigh from 1 to 100 kg. So you will have to see whether the machine is giving the accurate values over the entire operating range. Okay, so you just, so sometimes what may happen is, maybe if you have been frequently using this weighing machine for weighing somewhere near to 10 kgs, then in the 1 kg, in the 50 kg and 100 kg, the accuracy may be more, but in the 10 kg range, then the accuracy may not be there. So the linearity will give you an indication about how far your equipment is measuring, is accurate over the entire operating range. Okay, so it answers the question, does my gauge have the same accuracy across all reference values? Okay, then stability is the measure of how accurately the system performs over time. So that means what I do is, I do this linearity check now, then after 3 months, and then after 6 months, and then after 1 year, and then see whether there is a change in accuracy. If there is a change in accuracy over time for the same standard or same expected value, then means that is what we call it as a stability. That means the measurement is not stable. So the word bias or accuracy, linearity and stability are related to how far the actual readings are deviating from the expected value. Linearity is across the entire operating range, and stability is with respect to time. Okay. Then we talk about the other terminology, that is precision, repeatability and reproducibility. So precision is the closeness of agreement between independent measurements of a quantity under the same condition. So what do you mean by precision? Say for example, you just you measure a particular dimension of a rod. Suppose if it is giving the values like 10.10, 10.08, 10.05, 9.98, 9.95. So like that, you just make the 10 readings of the same part. Then whatever the difference in values we are getting, we call that as a precision. That means precision is an indication of how individual readings are closer to each other. So if it is precise means, say for example, if you are making the measurements of and the individual readings are closer to each other, we are making these individual readings and they are closer to each other, then we call this as a precise. Okay. So the precision indication of how the individual readings are closer to each other. Then repeatability is the variation due to the measuring device. It is the variation observed when the same operator measures the same part repeatedly with the same device. So, for example, now you are using the same measuring instrument, you are using the same part, and then same operator is making the repeated measurements. Whatever the difference we are getting, we call that as repeatability. And the reproducibility is a variation due to the measurement system. It is a variation observed when different operators measure the same part using the same device. So, when different operators are measuring the same part using the same device, whatever the difference is coming, we call that as reproducibility. So, I think if I put this in a pictorial format, then it will be easy for you to understanding. So, for example, you assume that we are doing this measurement system analysis, asking three operators A, B and C to do the trials. So each operator is doing two trials, trial 1 and trial 2, right? Then they are at each trial they are measuring 6 parts. Okay, that means the operator A will first measure the part 1 and then after some time he will measure the same part, right? So if you see the red indicated parts, so there the operator, say for example here the operator has got a value 10.10, same part is measuring again and then is getting 10.05, then whatever the difference we are getting, that is 0.05, is what we call it as repeatability. So repeatability is the difference in value when the same part is measured by the same operator. Same way, whenever we want to calculate the reproducibility, what we do is, it is like the green highlighted ones. That means the same part being measured by the different operators, operator A, operator B and operator C. So whatever the difference between these three readings, whatever you are getting, we call that as reproducibility. So what we have to remember is, repeatability is the difference whenever the same parts are being measured by the same operator using the same instrument, whereas reproducibility is the difference we are getting when the same parts are measured by the same instrument by different operators. Okay. So here this is actually the pictorial representation of the precision and precise and accurate. Say suppose now here you can see the individual readings are closer to each other, so we call that it is precise. But here the expected value is somewhere near the center. This is the expected value, the center of the circles. So since it is away from the expected value, but the individual readings are closer to each other, we call that this is precise but not accurate, right? Here the readings are almost closer to the expected values, but the individual readings are not closer to each other, so we call them, these are accurate but not precise. Here the individual readings are they are not closer to each other and they are also not closer to the expected value, so we call that as not accurate and not precise. So here in this last one, the individual readings are also closer to each other and they are also nearer to the expected value, so they are both accurate and precise. So whenever we are doing some measurements, we expect the measurements to be both accurate and precise. So here is what the decision whenever we are taking. So whenever here the MV is the measurement variation and the TSV is the total variance. So if the measurement variation is less than 10% of the total variation, then that is acceptable. If the measurement variation is 10 to 30% of the total variation, then it is marginally acceptable. But if the measurement variation is more than 30% of the total variation, then that is not acceptable. Then in that case, you will have to really see what is the problem, whether accuracy is the problem or precision is the problem. And then if accuracy is the problem, then you calibrate the instrument, and if precision is the problem, you give training to the people, or you just see whether you can make some changes in the measuring process. Okay. So now this table will give you the what is the accepted levels. So for the gauge R&R, so again I have given, like if it is 8%, then it is acceptable. 8 to 10% is we will have to accept its risk. More than 30% is not acceptable. So for whenever you are making the measurement system analysis for the discrete data, again all the accuracy, repeatability and reproducibility, all these three factors has to be more than 10%, 90%. Then only your measurement system is acceptable. So in this session, you have learnt about the precision and accuracy, bias, linearity and stability, gauge repeatability and reproducibility, and variable and attribute MSA, whatever is acceptable. So the summary of this session is that you will have to ensure that the measurement system is accurate, so that whatever the data you are generating for the project is accurate and there are no measurement errors. In this session, we are going to learn more about the process capability. So by the end of the session, you will be able to perform capability analysis, explain the concept of stability, define attribute and discrete capability, and illustrate the different monitoring techniques. In the last few sessions, we have learnt about the normal distribution. So I had told you that the understanding of the normal distribution is very, very important from the process capability point of view. So before going into the depth of process capability, I will just do a quick recap of what we learnt in the normal distribution. So if you can remember, we see a bell curve like this for any normal distributed parameters. Then we had the middle value, that is a mu, and then we found that within mu plus minus 3 sigma, that is sigma, 2 sigma, 3 sigma, minus sigma, minus 2 sigma and minus 3 sigma. So we were able to get almost 100% of the data within plus minus mu plus minus 3 sigma. So this we learned in the normal distribution. So the same thing I have just indicated here. If we see the minimum, we can just see this is the minus 3 sigma and this is plus 3 sigma and this is mu. So we call this 3 sigma level, we can call it as a UCL. We can call it as a UCL, that is the upper control limit. And this minus 3 sigma, we can call it as a LCL, that is the lower control limit. So here we can see this process. Whenever we talk about normally distributed process, that means we also saw that the process is running only with the chance variations or the common cause variations. So that means there is no special cost variations whenever the process is normally distributed. And we saw that whenever we are having this LSL is the lower specification limit, and the USL is the upper specification limit. So I will just give you an example for you to for easier understanding. Say for example, we are producing some circular rods with a diameter of 10 millimeter, and the customer says that he is willing to accept within plus minus 0.5 mm tolerance, that is 10 plus minus 0.5 mm is acceptable to him. Then in that case the LSL becomes 9.5 and USL becomes 10.5. Then assume that this is being processed in a machine, and we are just collecting some samples, and then we are calculating the mean and the standard deviation, and we are finding that the mean is 10 millimeters and the standard deviation sigma is equal to 0.1 millimeter. So in that case the UCL will be equal to 3 sigma, that is mu plus 3 sigma, that is equal to 10 plus 3 into 0.1, that is 10.3, and the LCL, that is equal to mu minus 3 sigma is equal to 10 minus 3 into 0.1, that is equal to 9.7. So here you can see that LCL we are coming to 9.7 and the UCL is 10.3. So here we find that the customer specification is between 9.5 and 10.5, whereas the process is producing from 9.7 to 10.3. So the possibility of any rejections is almost nil, and we will be able to always meet the customer specification. So whenever we are able to consistently meet the customer specification, then we say that the process is capable. So a process is capable when we are able to consistently meet customer requirements. Okay. So in this case we were able to meet the customer requirements. Say for example, if there was a problem in the machine and then the variation in the process had increased and then the sigma became 0.2, so in that case what will become? Then these wide variations will become like this. The LCL and UCL will get extended, and you find that we are producing some parts which are not meeting the specifications. So in that case the process is not capable of meeting the customer requirement. So from this slide what I expect you to understand is process capability can be measured only on processes which are stable. Stable means which are running only under the influence of the common cost variations. If there had been any special cost variations in the process, that should have been addressed before we start the capability analysis. And the second important point what you have to know is whenever your LCL and UCL are within the LSL and USL, that means the process is capable of producing the products as per the customer requirements. Whenever LCL and UCL are outside the LSL or USL, then that means we will not be able to, the process is not capable of meeting the customer requirements. Okay, so all along we have been telling that 6 sigma, so maybe you had been curious to know why we called it as a 6 sigma. So since the concept is new to you, I just waited till we learn about more on this normal distribution process capability, and this is the right time for you to explain why the terminology 6 sigma came into existence. Okay, so now say for example I just draw a process. So this is the LSL, that is the lower specification limit, and this is the USL, and this is the target value. And suppose if I am able to accommodate, and we saw that the 100% of the data points are lying between plus minus 3 sigma. So that is, this is minus sigma, minus 2 sigma, and this is minus 3 sigma, and this is sigma, 2 sigma, and 3 sigma. So assume that here the LCL and the UCL, that is the upper control limit and the upper specification limit are matching, and the lower control limit and lower specification limits are matching. So that means in this case the target to the specification limits, we are able to accommodate 3 standard deviations, 3 sigma, right? 1 sigma, 2 sigma, 3 sigma. So in a 3 sigma process, we are able to accommodate 3 standard deviations within the specification, within the target value and one of the specifications limit. So for example, if we are reducing the standard deviation in the process, and then we are able to accommodate 4 sigma, then what happens? Then again this LSL and the USL remains the same, because the customer has not changed the specification, but our process has improved, so that we are now able to accommodate 4 standard deviations within the LSL and this area. So this is minus 3 sigma, and this is plus 3 sigma, and this is 4 sigma, and this is minus 4 sigma. So that means what has happened is, now the variability in the process has reduced, and we are able to accommodate 4 standard deviations between the target value and the upper specification limit, right? So we called it as a 4 sigma process. And then we find that the probability of finding any errors, defective parts has really come down, right? Here almost maybe we are producing some parts which are defective, but here as the variability in the process has reduced, then the probability of producing any defect has come down. Now in a 6 sigma process, what has happened is, the variability in the process has been reduced to very large extent, so that within the target and the upper specification or lower specification, we are able to accommodate 6 standard deviations. Okay, so this is the lower specification limit, and this is the upper specification limit, and then what will happen is, this is actually the LCL and UCL. So that means the chances of a very defective product to be produced is becoming very, very less, and at this level we will be able to, we are producing only 33.4 parts per million defective parts. Whenever the process running at a 6 sigma level, that means you are able to accommodate 6 standard deviations between the target value and the upper specification limit. And when the process is running at a 6 sigma level, then we are producing only 3.4 defects per million opportunities. So this is how the name 6 sigma methodology has been derived out, because the variability in the process has been reduced to such a great extent that only a very minimum number of rejections are being produced from the process. So now, in order to really see how a process is performing, whether it is capable of meeting the customer requirements, then we need to measure the process performance. So the sigma is actually the measuring the process capability. So sigma level, we told that 2 sigma level, 3 sigma level, or 6 sigma level. Whenever we talk about the sigma level, you will have to understand that this is the measure for process capability. So whenever you are measuring the process capability, how we are going to measure the process capability will depend upon the type of data we are going to generate. I had clearly explained to you at the time of explaining the fundamentals of data, that understanding the data type is very, very important, because a lot of statistical tools will be based on the type of data we are going to use. Same way, the calculation of the process capability also will depend upon the data type. So for the variable data or the continuous data, we first calculate the CP CPK or PP PPK, and then from the calculation of these values, then we can calculate the sigma level. So this is the route we are taking for the continuous data. That means we first calculate the CP/CPK, and then from there we calculate the sigma level. How we are going to calculate the CP/CPK level, we will just see in the next few minutes. And for the attribute data, or we call that as the qualitative data. So in the define phase, we have just explained how we are going to calculate the DPMO. That means first we calculate what is the defect percentage. From there we calculate what is the DPU, then DPO, and then DPMO. That is the defects per million opportunity. Defects per million opportunities. And once we calculate the defects per million opportunities, then using the table, conversion table, we can convert the DPMO into sigma level. So irrespective of whether our starting data is continuous or the attribute data, finally we will be able to arrive at a single universal metric, that is the sigma level, for measuring the process capability. So the having a universal measure like sigma is very easy, because many times what happens is we take up a Six Sigma project for improvement of different types of metrics. So projects may be taken up to improve yield or improve the on-time delivery or reduce the rework. So the unit may be in time, cost, money, etc., etc. So it may be confusing if you are reporting the process performance in different units. But if you are going to have only a single unit for measuring the Six Sigma, for measuring the process capability, then all the projects can be reviewed in the same manner. So that is the advantage of having a universal metric like sigma. So even if 10 or 20 projects are running in the same company, first the individual project team has to first arrive at the current level of performance, what is the sigma level, and then based on their objective to which sigma level they want to go. So this is being done during the measure phase using the process capability analysis. Okay, so in the last slide I told you that for the continuous data we are going to measure the CP/CPK first, and then from there we will be able to arrive at the sigma level. So in this slide we will just see how we are going to calculate the CP. So the CP, we call that as a capability potential. That means what is the potential for the particular process. So it assumes that the process is centered at the target. Okay. So this may not be the reality, because in reality the process center may be away from the target also. But whenever you are calculating the CP, we are assuming that the process is settled at the target, and then see what is the potential for the project for the process to perform. So whenever you are calculating the CP, it does not consider where the process mean is lying. Okay, whether it is nearer to the target or away from the target, that information is not being used while calculating the CP. But why we are calculating the CP, I will explain you in a short while from now. So the formula for calculating CP is USL minus LSL divided by 6S. So USL minus LSL, we call it as a voice of customer, or this is the customer requirement. USL minus LSL, this was the customer requirement. And this 6x or 6 sigma, we call it as a process behavior. This is what the process is capable of producing. Say for example, in the example I gave you last time, the USL is 10.5, LSL is 9.5, and sigma is equal to, or S standard deviation is 0.1. Okay. So if you calculate the CP is equal to USL minus LSL divided by 6 into sigma. That is equal to 1 divided by 0.6, that is equal to 1.67. So this is how we calculate the CP. The CP we call it as a process potential index. Process potential index. So what does it CP means? That means the process is has the potential to produce the products with the level of 1.67. So here, if with respect to process capability meeting the customer requirements, then what should be the ideal CP values? So if CP is less than 1, so that means the process is having a poor capability. If it is from 1 to 1.5, so that means it is a marginal capability. If it is more than 1.5, it is good capability, and more than 2 means it is a Six Sigma capability. So since we are getting 1.67, that means we are somewhere in this range, means from good to in between good and Six Sigma capability. So higher the CP value, that is higher the CP value, better is the performance. Better is the performance. And if it is nearer to 2, then it is ideally it is the process is running at the Six Sigma level. Okay, so this is what we have to, higher the value of the CP, the better is the process. So I think you have clear understanding of what is CP. CP is the process potential index. So it tells you what is the potential of the process in meeting the customer requirements, assuming that the mean is at the target. Then we will just learn what is about the other metric. We call that as a CPK. So CPK is actually the process capability index. So process capability index. So if you really want to know what is the actual performance of the process, then we need to calculate the CPK. So the CPK will serve the purpose. So CPK measures how close you are to your target and how consistent you are in around the average performance. So whenever you are calculating the CPK, we are also seeing how the mean is lying nearer to the target value. So the formula for calculating the CPK is actually we calculate two values, and whichever is the lower of these two values, then we call that as the CPK. So the CPK, we will have to find the minimum of USL minus X bar divided by 3S or X bar minus LSL divided by 3S. So if you remember, maybe all along I have been telling mu and sigma. So this, if you are calculating the mean for the population, we call it as mu, and the standard deviation for the population, we call it sigma. Same thing, if you are going to measure in the samples, then the mean, if you calculate, then that becomes X bar, and the sigma becomes small s. Okay, so that is the reason why you are finding, I would have told USL minus mu divided by 3 sigma, whereas here it is indicated USL minus X bar divided by 3S. Okay, so then for the example I gave you, then how do you calculate the CPK? So first we will calculate these two values. So the first value is USL. So here again I just write down those values. USL is 10.5, LSL is 9.5, and X bar is 10, and S is 0.1. So USL is 10.5 minus X bar is 10 divided by 3 into 0.1, comma 10 minus 9.5 by 3 into 0.1, that is equal to 0.5 by 0.3 and 0.5 divided by 0.3, that's equal to 1.67 and 1.67. So then CPK becomes 1.67. So this is how we calculate the CPK using this formula. Okay, so the CPK will tell you what is the actual process performance. So CP was the process potential index, what is the process is having the potential to perform, whereas the CPK is the actual process performance. Okay, so now you may like to know if why we are calculating the CPK, because I had clearly told you that CPK will give you the right process performance, because this also considers where the mean is lying, whether it is nearer to the target or away from the target, that is also being considered. Then you will be curious to know then what is the purpose of calculating CP, what is the purpose of calculating CPK. So I will just explain to you with the example so that it becomes very clear to you. Okay. Okay, then I will just now explain this using 3 scenarios. So in scenario 1, we will keep the same parameters as what I explained to you. That means LSL is 9.5, USL is 10.5, mu is equal to 10 and sigma is equal to 0.1. Then while we are calculating the CP is equal to USL minus LSL, that is 10.5 minus 9.5 divided by 6 into 0.1, that is equal to 1 divided by 0.6, that is equal to 1.67. CPK is equal to 10.5. We will have to calculate these two values. 10.5 minus 10 divided by 3 into 0.1, comma 10 minus 9.5 divided by 3 into 0.1, that is equal to 0.5 by 0.3 and 0.5 by 0.3. That is the minimum of, that is equal to minimum of 1.67 and 1.67, that is equal to 1.67. So in case 1, I will just draw the picture here so that it will be very clear to you. So this is 10, this is 10.1, this is 10.2, and this is 10.3, this is 9.9, this is 9.8, and this is 9.7. And this is LSL, that is 9.5, and this is USL, that is 10.5. So this is you can just whatever is red in red, we call that as a scenario 1. So now I will explain you the scenario 2. So we assume that in the scenario 2, the LSL and USL remains the same, that is LSL is equal to 9.5 and USL is equal to 10.5, and mu is also the same, mu is equal to 10, but assume that the variability in the process has increased. So now sigma has become 0.2. So in that case, what happens? How do you calculate CP? CP is equal to 10.5 minus 9.5 divided by 6 into 0.2, that is equal to 1 divided by 1.2, that is equal to 0.884. CPK is equal to minimum of 10.5 minus 10 divided by 3 into 0.2, comma 10 minus 9.5 divided by 3 into 0.2, that is equal to minimum of 0.5 divided by 0.6, then 0.5 divided by 0.6, that is equal to 0.84. Okay. So if I indicate in this here in this process, it becomes, the process becomes from 9.4 to 10.6. So you find that some amount of rejections are being produced, out of spec materials are being produced. So that is the reason why CP and CPK have gone down. Okay. So this is scenario 2. Then let me put one more scenario, that is a scenario 3. So here again both LSL and USL remains the same. LSL is equal to 9.5, USL is equal to 10.5. But here assume that the mean has shifted far away from the target. You assume that mu is equal to 10.3 and the just 10.4, mu is equal to 10.4 and sigma remains the same as a scenario 1, that is 0.1. Then how do you calculate CP? CP is equal to 10.5 minus 9.5 divided by 6 into 0.1, that is equal to 1 divided by 0.6, that is equal to 1.67. What about CPK? CPK is equal to 10 minimum of 10.5 minus the mean is 10.4 divided by 3 into 0.1 comma 10.4 minus 10 divided by 3 into 0.1, that is equal to minimum of 0.1 divided by 0.3 and 0.4 divided by 0.3, that is equal to minimum of 0.33 and 1.33, that is equal to 1.33. So again if I indicate that in this this format, since the mean is 10.4, so the minimum will be 10.1 and the maximum will be 10.7. Okay, so you find that again lot more rejections are being taken care. So now if I summarize all these values in the table, so I'll just say write scenario 1, scenario number, then what is mu and what is sigma, and what is the value of CP, what is CPK. Just try to put the table. In scenario number 1, mu was 10, sigma was 0.1, CP was 1.67 and CPK was 1.67. So here in all the cases LSL was 9.5 and USL was 10.5. In scenario 2, mu is equal to 10, sigma is equal to 0.2, CP is 0.84, CPK is 0.84. So in 3, mu is equal to 10.4, sigma is equal to 0.1, CP is 1.67 and CPK is 0.33. Okay. So now if you compare scenario 1 and 2, so if you compare 1 and 2, what is really happening? You find that the mu remains the same. That means the process mean has not changed, but variability has increased. So variability has increased from, sigma has increased from 0.1 to 0.2. So that is the reason why the CP and CPK both have gone down, right? So for when compared to 1 and 2, the 2 is inferior, process 2 is inferior because of increase in variability. So we can find here that both CP and CPK are nearer to each other, right? Almost same. But we find that the CPK, both CP and CPK are nearer to each other. And then in the second case, CPK is lower. So the reason for the reduction of CP and CPK in scenario 2 is mainly because of the increase in the variability, right? When you compare process 1 and 3, we find that the variability is the same, right? The sigma is the same, 0.1 and 0.1. But again we find that the Cp is 1.67, that is very high, but Cpk is very low, that is 0.33. So that means again the process 3 is inferior because of mean shift. Okay? Because mean has shifted from, the target value is 10 and then the mean has shifted from 10 to 10.4. So that is the reason why the process 3 we are getting the low CPK, and then that is so the reason for the reduction in CPK value is because of the mean shift. So the calculating CP and CPK together will help you to identify what is the real problem, whether the real problem is increase in variability or mean shift. So if there is going to be an increase in variability, there will not be much difference between the CP and CPK value, and the one which is having the lower value, that means that the variability in the process is the problem. And if you are doing a Six Sigma project and you are finding that CP, CPK is both are low, but they are near to each other, then variability is the problem, and then you will have to study, analyze what are the reasons for the increased variability in the process, so that and try to take action to reduce the variability in the process, right? But suppose in case you are finding that there is a huge difference between CP and CPK value, right? Like in case 3, 1.67 is the CP and CPK is 0.33. So if there is a huge difference between the CP and CPK value, then the problem here is the mean shift. That means mean has shifted far away from the target value. So in your project, if you are getting a situation like this, then the action you should take is to find out the reasons which is driving the process to away from the target value. Then you will have to adjust those conditions so that the mean is brought in nearer to the target value. So in Six Sigma project, previously all along I have been telling you that Six Sigma methodology help you to reduce the variability. So now after doing the process capability study, you will also understand that there are two important aspects of improving the process capability. One is reducing the variability in the process, but equally important is also keeping mean nearer to target. So this is also very important. So whenever you are doing a Six Sigma project to improve your process, you will have to ensure that you are reducing the variability in the process and keep the mean of the process nearer to the target values. I think now the concept of process capability is very clear to you. Okay, now we have learnt about both CP and CPK. So in this slide we will learn about the relationship between the CP and CPK. So the first relationship what we need to know is CP is always greater than 0. So that means we cannot have a negative process capability values. So the second one is CPK is less than or equal to CP. So since in CP we are calculating the process potential index, and CPK we are measuring the process capability index, and we are not considering the mean, position of mean with respect to the target in calculating CP, always we find that CPK is always less than or equal to CP. You can never find a situation in which CP is more than CPK. So this relationship is very important, you will have to remember. And third one, the CP is actually the average of CPU and CPL, whereas CPK is the minimum of CPU and CPL. So that is the main difference. And fourth one, CPK is equal to 1 minus K into CP, where K is equal to 2 into determinant of U minus T divided by USL minus LSL. And K is always positive, so that you will find that 2 and 4 the relationships are matching. So these are all some of the important relationships about CP and CPK that you should remember. So now we have learnt about CP, CPK, which are the short-term process capability indices, and now we will learn about PP and PPK. So the PP and PPK are the long-term process capability indices,
we show the performance of a process over a longer period of time. So, what happens is whenever you are calculating the CP and CPK, we are just calculating the capability for the shorter period of time. Say, for example, you are taking the measurements within a shift, or within an operator, or within a particular batch within a particular batch. So, we always find CP or CPK during from the data collected over a shorter period of time, and then we collect that as a sample, and then from that sample we are trying to predict what is going to be the capability over a longer period of time. So that is why we are just taking the samples for a shorter period of time, and then this we are using to predict for a later how the process is going to behave. Okay, so that we call that as a short-term capability indices, CP and CPK. So now we are going to learn about the PP and PPK, which are the long-term process capability indices, and then this shows the performance of a process over a period of time. So that means this PP and PPK will also include the variabilities because of the special cause variations like difference in operators, or difference in batch of powder, or difference in machines, so that the PP PPK will always give you what was the performance based on the past data collected over a longer period of time. So CP CPK are short-term capabilities which are measured at a shorter period of time and which are going to predict how the performance is going to be over for a future, whereas PP and PPK are calculated from the data collected from the past data for a longer period of time, and which gives the actual capabilities of the process over a longer period of time, and which includes the whenever is running under both stable and unstable processes. So that means all the special cause variations are also accounted for whenever we are calculating the PP and PPK. So the PP PPK calculations includes effect of both common cause as well as the special cause variations. So how we are going to calculate this PP PPK? So here, instead of calculating the short term X bar and S, we are going to calculate the long term X bar and S. So that means instead of collecting samples over a shorter period of time, we are going to calculate the PP PPK based on the data collected over a longer period of time. So whenever we say it is a longer period of time, it is not that we are going to collect the data say for a week, within a month, or within a year or so. So it is not like that. So longer period of time means a period of time, this is enough to capture all the special cause variations. So it may be within a day, or within a week, or within a month, but we are very sure that this particular data will cover all the special cause variation that is bound to happen in this particular process. So longer period of time does not have any specification with respect to the time, but it will longer period of time means that all the special cause variations need to be accounted. So the process is considered to be capable if PP and PPK are greater than or equal to 1.33, and if the process PP is 2, then the process is performing at 6 sigma quality. So now we will just see the comparison between the CP and CPK and PP and PPK. So the CP and CPK are calculated using the sample data collected across a very narrow inference space and time, whereas the PP and PPK are calculated using data collected across a broad inference of space. So CP and CPK are sample data collected over a very short duration, so that's why we call that as a short-term process capability, whereas PP and PPK are calculated using data collected over a longer period of time, and then includes all the special cause variabilities also in the process. Then CP and CPK predict the performance of the process, whereas the PP and PPK will reflect how a process has performed during a specified period. And based on PP PPK, we will not be able to predict the future performance of the processes. Then the CP and CPK measure the best performance of a process under controlled conditions. So it represents the variability of only common cause variations, whereas the PP PPK provides realistic measures of performance and represents the variability of both common cause and special cause variations. Then CP and CPK are calculated using samples collected as subgroups, because what may happen is, okay, when the machine is running, maybe we will collect 5 or 10 numbers every hour, and then we will calculate the CP CPK based on those 10 number samples. So this 10 number sample is considered to be a subgroup. So every time, every hour we are collecting 10 numbers, and then for each 10 numbers you are going to calculate the CP CPK. We call that as a subgroup. Whereas in the PP PPK we do not have a concept of subgroup, and then this is collected from the data over a longer period of time. Maybe we will collect, if we collect the data for say 1 week, maybe we are having 400 500 data points, and using those 400 500 data points we have to calculate the PP PPK. So there is no concept of any subgroup whenever you are calculating the PP and PPK. So here is an example of the output from Minitab for the process capability studies. So once we input the data into Minitab and then we do the process capability analysis, this is what will be the output. So from here you can find that you will be able to calculate the value of CP CPK. So we find that the CP is within the short term, and the CPK, the CP CPK are within short term, and whereas PP PPK are over a long term. So this within indicates the overall data as many subgroups used to calculate CPK.
Okay, so whenever we measure the CP and CPK and then get the CP CPK values, then there are different reactions that are possible. One thing is, okay, you can just do nothing. So if the process is well within the specifications, then maybe we need not have to do anything, so the process can continue. Suppose we find that again the process is not meeting the required specifications, and then we feel that it may not be possible for us to improve the process, then we can request the customer to see whether the specifications can be changed, so that we will be able to produce the products as per the specification. Or if we feel that there is a possibility to improve the process and we are feeling that the centering of the mean was a problem, then you can try to bring the mean nearer to the center value. Or if you find that the variability is the process, then you can just try to take some actions to reduce the variability. Or finally, you can just maybe accept the losses, saying that okay, we cannot do anything about it, we cannot change the specification, we cannot improve the process, so this is how it has to run. So normally this type of approach is not taken for Six Sigma, and if the customer is not willing to change the specification, so this is also ruled out. So this is also ruled out, because we cannot, even if because if already the process is running in a good condition, we would not have taken it up as a Six Sigma. So normally in a Six Sigma project, we are trying to do this, either trying to center the process nearer to the target value or reduce the variability. So these are the other applications where the capability study can be useful. So provide a basis to set up a variable control chart. So whenever we are improve the process and then we hand over to the production, then we will have to monitor whether the process is performing as per the improved standards. So that is, we control it through the control chart, which we will be learning in detail in the control phase. Then whenever we are evaluating a new equipment, suppose you have got a new machine and then you want to really check whether the new machine is capable of producing as per the customer specification, then you can use this process capability study. Then reviewing tolerance based on the inherent validity of process. So this is what again the case number 2 here. Say for example, you are running the process and then find that with the best possible efforts you are getting always getting the products less than the specification, out of specification. Then maybe you can just review whether the tolerance can be increased, so that then you'll have to again contact the customer if he is willing for doing that. Otherwise, in some cases, assigning more capable equipment to tougher jobs. Sometimes it may happen that the customer specifications may be too stringent and your normal machine is not capable of delivering that particular product. Then maybe you'll have to allocate some high precision machines for doing such type of job. So that type of decision can be taken by doing the capability study. Then it will also help for performing the routine audits and then determining the effects of adjustment during processing. So what type of adjustments we should do at the time of producing, whether we need to adjust the process to bring the mean nearer to the center or adjust the process to reduce the variability in the process. So that type of decision can be taken by doing the capability analysis. Okay, so on which type of process measures will you do a process capability study? So the first requirement is that it should be a indicative of a key factor for the quality of the product or process. So for example, now we are measuring the on-time delivery time, and then we feel that it is an important factor to be delivered to the customer. So that is the reason why we are measuring that. Okay. So we do the process capability study only on the parameters or characteristics which is going to be a key measurement for measuring the quality of the product or service. Then it should be possible to adjust the value of the characteristics. So depending upon once we get the capability values, then we should be able to adjust the process in order to meet the requirement. As I told you, either we should be able to shift the mean or reduce the variability in the process by doing some adjustments in the process condition. Then the operators conditions that affect the measured characteristics should be defined and controlled. That means whenever you are doing the process capability study, we should always do it in a controlled atmosphere surrounding. That means whatever the process conditions that need to be monitored and controlled, that has to be strictly monitored and controlled at the time of making this process capability study. So how do you fix the tolerances and specifications? Either they are the customer specific requirements, so we cannot change, or these are industry standards, or this is the organization's own engineering department. So we will have the flexibility of adjusting the tolerance only if it is fixed by the engineering department, but if it is a customer requirement and the customer is not in a position to change, then we will go by the customer requirements as the tolerances while we are measuring the process capability.
When we were learning about the basics of Six Sigma on the first session, we learnt about two types of variation. One is the variations due to the common causes, and the other one is the variation due to special causes. Common cause variations and special cause variations. So common cause variations are the variations which are inherent to the process and which are giving us a permanent problem, whereas special cause variations are one-time efforts. Even though they have a major impact on certain days, then it is not a chronic problem. And we also learned that Six Sigma methodology helps you to solve the problems because of the common causes. Okay. Now we will just try to understand what is the concept of stability. So whenever we talk about the stability of the process, or we want to check whether the process is stable or not, we consider that a process is stable only if it is running under the influence of the common cause variations, and there are no special cause variations are there in the process. So whenever we are making improvement in a process, or whenever we are collecting the data, so first thing we'll have to ensure is that a process is stable. So how do you ensure that? Again, there are two ways we can check whether the process is stable. So whenever we are in the initial stages of the project and we are collecting the data, first you take the help of run charts. So these run charts, we learnt about it when we were talking about the graphical tools. So the run charts will able to help you to check whether the process is stable. So whenever you are plotting the run chart, if you are not finding any trends or patterns when the particular metric is measured against time, then we call that the process is stable. But if there is a pattern like increasing trend or reducing trend, of any patterns are there in the run chart, that means the process is not in control and it is running under the influence of special cause variation. So after the project is completed, then we use the control charts. We use the control charts to check whether the process is stable. So the control charts is nothing but similar to a run chart, but the only difference is that it has a statistically determined LCL and UCL values, lower control limit and upper control limit, and then we are just plotting the measuring that particular metric and then seeing whether the variation is lying within LCL and UCL. The individual readings do not go out of the control limits, and also there are no patterns over a longer period of time. So this is how we are controlling the process through control chart. So both run charts and control charts will give an idea about whether the process is stable or not. Okay, so again the stability we can of process, again we can just control by knowing what is the data type. So if you are dealing with defects or defectives, that means when the data is attribute, then we are using the control charts, the P chart and the NP chart we use to see whether the process is in control, and whenever you are measuring the defectives. And we use the C chart and U chart whenever we are controlling the defects. So here the control chart represents the process capability once special causes have been identified and removed from the process, and then once you plot the P chart and NP chart whenever you are measuring the defectives and we are not seeing any individual readings going above or below the control limits and there is no visible pattern, then we can say that the process is in control. Same way, whenever you are plotting the defects against the time in the control chart using C chart and U chart, if any individual readings are not going above or below the control limits and if there is no pattern, then we can call that process is under control. So these four charts help us to control the process and check the stability of the process when we are measuring the defectives and defects. So for the variable data, we will have to first check whether the data is normal. So whenever you are checking the normality of the data, we have seen in whenever we learned about the normal distribution curve that whenever the process is stable, then we tend to get a bell-shaped curve for the distribution. And then in order to check the normality, we do the normality check by using a probability plot of the normal, and if the p-value is more than 0.05, then we can assume that the data is normal. So if the data is normal, so that means the process is running under the influence of common cause variations only. And then for the variable data, whenever we are measuring some metrics and then we want to control, then we take the help of the normal distribution. So any process output has an inherent variation that is normal. So whenever we learned about the normal distribution, we saw that 100% of the data points were lying between -3 sigma and +3 sigma. So that much of variation is always inherent in the process. So the natural process limits are also known as the natural process variation or the normal process variation. So in a normally distributed data, ±3 sigma limit spreads around the process average and covers 99.73% of process variation. So 99.73% of the total process variation lies within ±3 sigma whenever the process is running under the influence of only the common cause variation or whenever the distribution is normal. So like how we were using the P chart, NP chart, U chart and C chart for the control charts for attribute data, similarly we are using several charts for the variable data. So whenever we are going to have a sample size between 5 and 8, then we use the X bar R chart. So about the control charts we will learn more whenever we are covering the SPC in the control phase. But here we will just see whenever you are plotting the X bar R chart, again this will help you to find out whether the process is in control, and we will have to check whether any readings are above or below the control limits and if there is any patterns. If the individual points are above and below the central line, randomly distributed without any pattern, then we call that the process is stable. So this is how we check whether a process is stable whenever we are measuring a output as a variable data. So this is actually a chart which shows both the process capability and the process stability we are trying to capture in the single sheet of single frame. So here the X bar R chart will tell you whether the process is stable. So to check whether the process is stable, we check whether any points are above or below the control limits and if there are any visible patterns. So ideally we should get points which are not distributed randomly above and below the middle line, randomly distributed. And for a normal for the variable data, again for the process stability, we can also check about the normality. If the data is normal, then we will the process is running under the confluence of only the common cause variation and the process is stable. And then for calculating the process capability, then we use the CP/CPK formula, and once you know the values of CP/CPK, then we will be able to know how far the process is capable. So the process capability is measured in terms of CP/CPK, and the process stability is measured using the control chart. So whenever we want to improve the process, then we'll have to ensure that both the process is stable as well as process is capable. Stability means that the process is not under the influence of any special cause variation, and capability means we are able to always produce the parts as per the customer requirements without producing any major defects. Now let us learn about the attribute and discrete capability. So till now we have been learning about finding the capability values for the continuous data, the CP, CPK or PP, PPK, whatever you are calculating for measuring the process capability was for the continuous data, where we are measuring some parameters and noting down the measured values. So now we will learn about the process capability for discrete data and attribute data. So mostly the attribute data for which we are calculating the capability, we do the calculation for the defects, and defectives. So the difference between defectives and defects is that suppose a part may be having multiple defects. Say for example we are checking a electronic component, capacitor you can say. So there are different ways in which there are different defects may come into the capacitor. So there may be a problem in the capacitance value, there may be a physical defect like a chip off or a crack. So these are all we call as defects. So the defects are normally counted. Whereas if part is if a capacitor is found to be having a low or a higher capacitance when compared to the specifications, or if we are finding any chip offs or cracks and we reject it, then we call that capacitor as a defective. Okay, so defective is actually when the entire part is rejected, we call it as a defective item, and then a defective item can have multiple defects. So that is the difference between defects and defectives. So whenever we are plotting the capability, then whenever we are trying to find the capability, whenever we are measuring the defectives, then we take the help of the binomial capability analysis. We do the binomial capability analysis whenever the data are having the number of defective items out of the total number sample. So what are the different conditions which apply for doing the binomial capability analysis? Are each item can result in only one or two possible outcomes. So there are only two possible outcomes, either pass or fail, yes or no. So either it is accepted or rejected. So whatever is rejected is the defective. So when such conditions occur, then we call that as a binomial distribution, and then we will be able to use the binomial capability analysis. The second condition is that the probability of success or a failure is constant for each item. That means it does not change over time. And the third one is the outcomes of the items are independent of each other. So if you are having 100 items and we are trying to find out what is the defective items, then the point that one item is defective does not have any impact on the other item. So that means each and every part is independent of each other. So that's why we call that the outcomes of the items are independent of each other. So if these three conditions apply, that means whenever the outcome is having only two possible outcomes, yes or no, then whenever the probability of success is constant for each item, and third, all the items are independent of each other, then we can use the binomial capability analysis. And then using the Minitab, we can go to this particular menu, Stat, Quality Tools, Capability Analysis and Binomial. Then we can just put the data into the Minitab, and then the output will be like this, the binomial process capability of defective, where you will also get the P chart, and then we also get the what is the summary status, what is the percentage effective, what is the lower confidence interval, upper confidence interval. So all those informations will come. So this will give us an idea whether the process is capable or not. Similarly, whenever we are doing the capability analysis on defects, then we use the attribute capability Poisson. So Poisson capability analysis is used when data are the number of defects in an item, where the item occupied a specified amount of time or a specified space. So the conditions which apply for the Poisson capability analysis are, the first one is the rate of defects per unit space or time is the same for each item, and the number of defects observed in the items are independent of each other. So if these two conditions are met, then we can apply the Poisson capability analysis. And then again we just collect the data and then input the data in this menu, in Minitab, Stat, Quality Tools, Capability Analysis, Poisson, and then you will get a output like this. So where also you will get the U chart, and also you will get the lower and upper confidence intervals. So from this we will be able to find out the capability of the Poisson capability analysis. So we'll have to, if any points are going out of the UCL or LCL, that means the process is not capable.